Welcome to another video. In the last video we looked at how types are lowered into the egg, and this time we'll look at functions. And down here, this is what we'll look at next. Maybe let me just write the section header for that. So in this to yogurt thing, what do we do here? We just have, damn, this is a long file. This is really long. Looking up functions in the egg. We kind of... No, we don't do that. Well, but I think we'll need to do something like that, actually. Yeah, so looking up functions is like a big thing that we need to support. Oh man. Oh man. A lot of that, like the egg kind of needs to do what the egg already did, plus part of what you're converting egg to yogurt does, but it's not as difficult as that. Like these casts here, and we don't need to do comptime casts and runtime casts and so on. Like, we don't have cast functions that we call. We are still working on a higher level, so yeah. At least we got that going for us. Right. Compiling code to run at runtime. this is a lot of stuff that's going on here. I think lambdas are simpler in our case. They are not separate functions, so they, you know, we don't need to collect like captured variables or something. But damn, there's a lot of stuff. Okay, yeah, these cast functions, compilations, these, like, we don't need those. We really don't need those. So that's nice. And that's already like 100, not 100 lines, but 1088. Oh, it is more than 100. Way more. You know what? Let me maybe kind of convert, or like rather than having this one huge file within some of these sections having no internal structure, let's convert this into a module. Let's say we have, what is it, bacon, no, toast to egg. Let's say we have a folder, toast to egg. Yeah. Then our toast to egg is in that folder. And let's call that a mod, similar to as in Rust. You know, like mod is the main entry point of that folder. But now we can factor stuff out. We can say, you know, variable scoping. That's a separate thing. Hang on, visible. And this would import .dot/pam.mal. This part can be a completely separate file. Clean. Nice. Yeah, simple variable scoping. Then compiling types. Again, like this is somewhat, you know, like somewhat closed thing. Hell yeah. That is nice. That is really nice. I think I'll actually do the same thing for like parsing and maybe for some of the other stages. Yeah. Right now I'm kind of, you know, basically what I'm trying to do is I have this compiler pipeline and the intermediate abstractions that exist, they are basically finished. Well, you know, there's some stuff that is still a bit vague with regards to comptime evaluation, and I want to shift more of that into the egg rather than the yogurt. But apart from that, like the things I need to do in this compiler pipeline, I've basically figured those out. So now I'm more in the mode of, you know, trying to think of where can I let's build this a bit cleaner. Let's shuffle this around. Let's do not just name, like let's do function resolution already in this compiler stage. Let's do that there, over there. Like shuffling these kind of around until I found a good abstraction that from this compiler stage to this other compiler stage, all of that happens, and then in that other compiler stage, then the next stuff happens. Basically, I'm cleaning up how that works and figuring out what are good abstractions. Yeah. So it makes sense that I'm like creating new folders and dealing with all that. Cool. Yeah. What else can I do? I can perhaps at some point in here, yeah, we try to import that, and that doesn't exist anymore. So instead we import the mod file. So basically previously what we did is this, looking up functions. And I think it makes sense to put that in its own file as well. And some sort of a lookup. I like that. Oh yeah, this, I've moved that. And especially this part here no longer exists. The other part is adapted into the types thing. So yeah. This is like the main compilation, I guess. So let's put that in its own file. Why not? but not today. So, yeah. Okay, so in the next part, I didn't realize that the microphone wasn't working. I still left that in, but feel free to skip that. Well, turns out I didn't really have my mic working, so I think now that's fixed. What I did is basically I refactored the lookup of the functions, which has now its own file. We have a matching thing for testing whether the toast signature matches a given name and arguments. And the lookup is now supposed to look up a function in a given module with given toasts, meaning that it will also look at imports, for example, and see if they match the function signature and do stuff like that. Okay, so first of all, functions within the same module should also match. You should be able to call functions defined in the same module. So we'll create toast signatures for those, consisting of a name, which is the function name, and arguments, which will be the function arguments lowered to like font types, I suppose. Yeah, which will be a list of font types, and then we do fun dot, well, no, for each argument of the function, we just push that into this list. I'm compiling that using the types that we now also need to accept. Okay, and then we return slice to that. Okay, and this toast signature with this name and these arguments, this kind of describes this, the signature of this locally defined function. And then that function should match yeah, it should match our name and arguments that we provide, like that. If that's the case, then we'll need to do something. Yeah, I'm not entirely sure how, like, we return a matching fun, but a matching fun contains an egg fun. That is probably not what we want to do. Instead, we want to return a toast fun, because then that function might still have to be like compiled or constant folded or whatever. Yeah. Okay, so what do we do here? I guess we should just have a list of global functions, maybe. I'm not entirely sure, to be honest. Yeah, kind of matches, maybe. And that will be, well, matching funds, maybe. That will be a list of toast funds. And then in here we can, let's kind of refactor that code to be a bit less what it is currently. So we build a toast signature, and then we check if this signature matches our named arguments. Then we add the original function to this list of matching functions. Something like that. Okay, and then for the import, well, we go through the individual import parts. We resolve the module. Yeah, we go through the signatures in there, and then we oh yeah, if this is a function signature, not a type signature, which is really not elegant here, then we want to check if that signature matches. So basically matches, yeah, this one right here. So we do signature matches our name and args using these types. If that's the case, then, and this is pretty cool, like this, you're only resolving imports when they actually match, allows us to have this kind of granular circular using of functions across multiple modules. You may have two modules and one module defines some very fundamental function that another module then imports and uses, but then the first module also imports this other function from the second module, and so on. Like you can have these kind of interwoven functions, because we don't do this sort of let's resolve all exports of a module, which may not even be possible because they depend on exports that depend on exports. Like, you know, rather we do that on an individual per function basis, and we only look for functions on demand, basically. So here we resolve the import, we assert that args have different names. Yeah, like this is something that we should do, maybe at some point. I don't know. I'm just gonna comment this out, I think. And yeah, if the signature matches, then this is a valid function that should be added to this matching funds list. It definitely should be added here. Yeah. Oh, okay, so that is cool. We don't even need other modules, do we? No, because we have all the information for matching functions in the import signature directly. We don't even need to know the content of other modules. That is nice. That is really nice. Okay, let's maybe simplify things even further. Let's maybe first build some sort of map of function not signatures, you know, but function gather funds. Horrible naming, I need to fix that. But basically a list of, you know, from the function signature to the actual function, but in a self-contained way within a module, without needing to look at other modules. So this would actually be a fun in scope or something. And fun in scope is defined as either a local function defined directly in here, so host fun, or it is an imported function. And then we can kind of build this, similar to what we do with types, you know, build this kind of map of all types. I'm not sure where that is, but yeah, this kind of map from string to the type definition, and the string contains the module. So basically, if you import a function in this map, there will be a function. I don't know. We have the int module, for example, which imports the plus function from strings. That would mean that in this map there should be an entry for like plus function, like core.int.plus, taking a string into string. But that just refers to another module's function. Yeah. Okay, so yeah, somehow that. Actually, let's split this into, let's say we have the fun in scope, which has a name and args, which will be plum types, and it has an implementation. Let's call it, yeah, visible fun, maybe. Then the implementation can either be a local toast function defined directly here, or an imported function. Yeah, and this returns a map from these kind of strings to visible functions. Damn, okay. That means without even checking a function match some other function, what we can do is similar to what we did with types, compile all types. We have not compile all functions, but collect all functions. And yeah, we can then let's pass the toasts in here maybe, and the types. So this should be. And what we do is we iterate over the toasts. I feel like I did this like several times. Hang on. Yeah, compiling an individual toast fun, that is true. Something to egg. Yeah, this is what I want. Iterating over the toasts, building up these kind of, it's called uncompiled fun. Yeah. Let's see. I mean, uncompiled fun is also, I'm gonna call it visible fun for now. So basically for every entry in the toasts, we get the module, we get the toast, and then rather than this, we just iterate over the toast definitions. If it's a function, then we want to put that into this map. So what we do is we put in there a visible fun, and we compile the arguments. So something like this. Params is actually the better term for that, I think. Yeah, so we have a visible fun that contains a name contains params, which is a slice of parameters, and it contains an impl, which is a visible fun impl dot local of that toast fun, like that, without even needing to compile something to anything else. Yeah, that's cool. Also, instead of this switch, let's make, instead of this if, let's switch on the definition. If it's a fun, then we do that. If it's an import, we do something similar actually. Yeah, this is a general theme, I think. So we also build a signature, which will be the current module, followed by the function name. Let's maybe put a slash or dot in there. No. Fun.name.string. Although this, of course, is import. Like the import is complicated with parts and stuff, so let's get this first. Yeah. So we have the imported module. Yeah, we want to do this more elegantly. Here we don't even do anything crazy, we just check that. So we have signature string, which is the module, and it contains the the name. And then it also needs to lower the parameters. Oh, I think this is like compile using the types. Something like that. And then we put those in here. So basically, to these functions, we put our signature string, the visible function with the name, the parameters, and the implementation will be an imported function. So this is like our signature. And the referred signature is just the imported module containing the signature name. I'm just realizing we also need to allow overloading, we also need to put the parameter types in there. Well, okay, yeah. Cool. Yeah. And in the end, we have this map from string to visible fun of these funs. Amazing. And we didn't need to do any sort of matching yet. Okay, that is actually cool. Collect all funds. Let's try that out. Collect funds. Let's collect all funds. Well, collect all funds. We have the toasts, and we have the types. And then for every funds, we kind of want to print that. Yeah, this debug is gonna bite us in the ass, but yeah. Okay, you know what, let's print only the name. The value is the actual visible fun, which has a name, which has a string, and then entry value params. Yeah, something like that. Yeah, let's also open up a terminal because I restarted my PC when trying to fix the mic. 286. We are somewhere here. Oh yeah, this doesn't make any sense. Feels like there's some sort of mismatch of these braces, perhaps. Matching fun is this. Expected closing brace. Yeah, that doesn't really match this one, but this one, this looks fine, this doesn't look fine. Okay, so for every part we do something. Let's maybe fold this. This is one giant if with this closing curly brace. Yeah, that is nicely and correctly indented. By the way, these are the kind of errors that can't happen in Plump because everything is indentation based. Like figuring out these closing braces and where they need to go and stuff like that. That's not something that you need to do. Yeah, but this looks correct, I think. This one and this one closes the function. Yeah, okay. Let's give this another try. Yeah, other cases are not handled, but that is fine because they don't introduce any visible functions. Okay, so we have this compile of a type, but here we have a map from string to plumb type. Here we have a list of ongoing calls. Here we have an int and a map and other stuff. Let's see, toast type. Def. I don't know what's going on here. Compile a module. Oh, I see. The types don't really have a nice way of compiling them. Like, there was compile all types. Yeah. Hang on. So we have this prefix calls thing. We have this one, compile a type. Which is only used to kind of generate this this map. that we get from here. And then using that map, you should be able to compile types more efficiently, you know. So given a toast type, and probably an environment, because you should be able to compile it into type. Oh no, so so basically we should switch on the type and do something very similar to this, I think. I don't like that, to be honest. It does seem wrong. Oh yeah, here we don't have a toast type, we have a plum type, I think. Hang on. Compile all funds. Collect all funds. So if we have a function, then what we do is we take those parameter types, which are toast types, yeah, so we should be able to compile them to plum types. Why is this so weird? Well, okay, so type variable should just do that. Why is there so much duplication here? That does not seem like the correct thing. Okay, you know what, let's add some sort of okay, I have a plan. I have this comment in the where somewhere here I have a comment for calls, I think. Maybe not. Maybe it's it's down here, maybe? Yeah, this one. So rather than compiling all the types completely isolated from each other, I think we want to allow them to access this kind of dictionary of how a type's defined directly. And I think once we have that, and once we integrate that into this function up here, then it's also easy to write a wrapper around this function that doesn't even depend on the toast type defs anymore, but just uses that kind of cache that is guaranteed to contain all the types. So basically, let's say we have some sort of cache from string to some type. Yeah, nothing changes for variables, nothing. And well, for calls, things change, yeah. So we lower the arguments. Oh yeah, and I think this cache should actually contain not just a plum type, but a kind of, I don't know, plum type definition, which doesn't really exist yet. There's something that has a that also has parameters. And then this down here, instead of just building a map of plum type, actually returns a list of plum type defs. Then here we have plum type defs. We build an environment, we have arguments, we compile stuff. And in the end, we compile those plum type defs. Yeah, and in here, we put not just the we put in here a plum type def containing the strings and then in here we have the params and the actual type, which is this. Yeah, something like that. Yeah, this compile thing now also expects these defs, so kind of the cache, you know. Let's call it, yeah, I don't know, compiled defs. Mutable thing. Yeah. basically for calls, we can now check before accessing the definitions, we basically want to look into the cache. So yeah, we've lowered the arguments. And then if cache contains oh, this is weird. This is weird. I don't like that. I really don't like that. All of the code gets more complicated. Nah. I do like having plum type defs. Yeah. But I don't like having this kind of cache that gets passed around to. This is kind of weird. Okay, so I think what we need to do is I'm gonna do the obvious, well, not obvious, but the stupid, simple thing, even though it's a lot more code and some duplicated code. And that's just to create a version of this function that expects types rather than the toast type definitions. So one that accepts plum type definitions. Basically already compiled type definitions. Yeah. If this is a type variable, then this really is a type variable. It's not like $something. I'm not sure about that. Yeah, but basically we know that these I don't know. This is probably fine. Instead of defs, we pass around types. I mean, actually defs is an okay name for that, you know. Yeah, we lower the arguments. We know that we are not recursively lowering a type, because all of these definitions, they are self-contained. So we never need to do this. Yeah, now we're only looking at like type literals in your code, type expressions like int, or a struct containing an int and a foo. and we have this kind of dictionary that tells us for each of these, you know, named types how they are defined. Yeah. Okay, so we can just we know that you cannot express a recursive type just by itself. You have to use named types to kind of create that recursion. Yeah, call the def. This is a plum type. We check that it has the correct amount of parameters, and then we want to specialize that plum type for our types. Yeah, we don't need this, we don't need parent calls, we don't need depth, because we know that these are not recursive. Boom. We have a type, we have an environment. And we have type definitions. Wondering, do we need that environment? Maybe not. Yeah, I think the environment is only used for yeah, I think there should be a way to specialize types later on. So we don't need to do that in here up front. Yeah. Compile a type using definitions. Okay, yeah, type variables, they are just mapped to themselves instead of this, I think. So this will just be a, you know, a plum type or primitive of that string. Yeah, for a call, we lower the arguments, makes sense. Just using the definitions. We look for a type with a name. We check that the length matches. And then we kind of need to specialize that. So specialize using some environment. I think types already have some sort of specialized thing. Yeah, a plum type with substitutions, and substitutions is defined as this, a map from string to plum type. Okay, this. specialize cannot fail, right? Yeah, that's cool. Okay. So now this should work. Collect all funds doesn't work because it expects plum type defs. That is indeed true. So we call it type defs. Yeah, let's call it types. I think that's fine. Yeah. This is much simpler. It's just the type definitions. Same here. And here, well, in lookup. Hang on. Toast to egg lookup, line 24. Collect all funds. Oh yeah, that can fail if the function has like invalid types. Makes sense. Yeah, and it returns an OK down here, so cool. Invisible fun is not a struct type. Oh, indeed. But it should be. Ah, yeah. Hang on, where's that? 34. Here. Oh, oh. Hey, so params is not a field on toast signature. Only contains these fields. Name it args. Oh yeah. This is directly a type. Makes sense. Compiles at least. That's something. Okay, I think types need to be prefixed with the module. So we'll probably want some sort of function like compile a type in a module using these type definitions. And what that does is it takes the type, it kind of a prefix calls the module, and then compiles that with those definitions. And in the lookup thing, when we compile that, we actually want to look up that in the compiled module. Hang on, like compile is also called here. Okay, so in the never module, hang on, let's actually look at that. Never. Indeed. Oh no, hang on. We import built-ins, and from that we import this function, the crash function that takes a string. And we try to export the crash function taking a string. But that crash function taking a string doesn't exist because string is not even defined here. Makes sense? That is cool. Like this is, it's good that this raises an error, you know. So actually, we also want to import the string type. Oh, I think this is parsed as int taking an int as an argument, maybe? That would be kind of bad. Let's see, parse signature is what we have. I think this should be just type atom, so type without any white space inside. Well, you know, except it's... Whew, okay. This is something. So what do we have here? We have kind of traversed all the modules, and we've created these kind of functions that can either be implemented directly in here as functions, or they can refer to other functions. So let's see, we have this subints function. It refers to the name subints. Not sure if that's correct. Well, okay, I'm taking two integers. We have this or function referring to this or function taking two integers. And the cool thing is that now we don't, like previously when we looked for a function, we would try to compile the types of those functions and try to match them. Now we just do that once. We go over all functions, we compile their types, and using this, it should then be possible to compile the code fairly easily, you know, because we have this giant list of functions with unique names, because they are prefixed with a module, and with the concrete plum types that they accept. Okay, you know. So maybe rather than okay, so there are a few things that I want to improve. First of all, I think the signature is not perfect. Yeah, I think I want more types there, kind of. Okay, let's maybe first print something that's a bit more helpful than just than this. And because the name is kind of implied in the key, so let's remove that. And instead, let's just switch on the implementation. If it is like a local function, we'll just print local. And if it's imported, then we'll write imported. And this way, we should kind of be able to see where the function is coming from. Oh yeah, for the imported one, let's actually print the signature. Yeah. Okay, so we have all functions, and we can now see that we have this subints function taking two integers. And actually, it just refers to the builtins.subints function. We have this core.or function. Actually, it refers to core.int.or. Oh yeah, the or function taking two ints comes from the int module. And then let's look for the int or function. Here are some int functions. Int or. Yeah, the int or function is defined locally within this module. Okay. So we kind of have this map of what is the function, you know, the global function ID basically, and how is that defined. Cool. Now this ID should also contain the the parameters. Yeah, so I'm gonna look at that next. Yeah, the types kind of need to go into the signature. But at the same time, they should be kind of normalized. Well, you know, let's just put them into the signature, and then we'll see what happens. Okay, so in the lookup thing, at some points, yeah, we built the signature, both here, but also down here and down here. Let's maybe create a signature for that. Signature where the function in a module, we give a name and the params. So the signature will just be the concatenation of the, let's create a string builder maybe. And then print the module dot the name, and then for every param we also print the param. We return that, and then down here we can say signature is just the signature of the module, and the from name and these params, which we need to know before. And similarly in here we have our signature and the referred signature, but they depend on the params. So here we can just do signature of module and signature name string and params. And this will be signature imported module, signature name string and params. Okay. Yeah. So now the function signatures, they also contain the types, which means in here we don't really need to print them again. Okay. So we have a bunch of functions. And we can see that for example, the core.star function taking an int and an int is really just the core int star function taking an int and an int. And the core int star function taking an int and an int is a local function defined in there. That's pretty cool. Yeah, I like that. Okay. Yeah, we don't really validate that those functions exist yet. But I think let's just try to compile functions now. Because now we have this map of global functions, we should be able to compile them. So for every function in there, well, yeah, that's actually a map entry with the key being the signature and the function being the value. Now we should be able to compile that function. Let's not do stuff like this. We want to create some sort of map from string to eggfuns, and we want to compile these functions and then put them into that map. And of course this may need the... Does that need stuff? I'm actually not sure. Yeah, probably other functions to get their signatures and return values and maybe evaluate them and stuff like that. Okay, so we have compile. Compile a visible function. using this other thing. Yeah. So I think this should compile this. Oh, hang on, it's a visible fun. What is a visible fun again? A visible fun has a name. Sure, it has that, and it has an impl. I don't know. Compile fun. Let's do toast fun. Yeah, with a map of visible funs. And then in here we can we pass these visible funs, but here we'll take the inner, what is it, the inner impl dot local. Oh yeah, we only need to compile local functions. So if fun dot impl is local, if that's a local function, then we'll compile it and add that to the map. Okay. Yeah, like that. So fun.impl. Impl is not a field on toast fun. Yes, that is true. Okay, now we're in compile fun. That's cool. Yeah, let's just leave that to do there and see how that works out. Amazing. So we start by compiling round up to power of rec. Nice. Because that's the first local function. Yeah. So this is the place where we actually compile the function. We now have a map of all visible functions. We know which module this function is from, so we can, in theory, get the functions that are visible. Oh yeah, I think this is really just a list of all functions. Yeah, the visible ones we kind of need to provide a set of invisible functions here. Okay, yeah. Which means that for this function we need to check which of these, which functions are visible. Okay, you know what? Let's maybe rename this to like uncompiled fun. After all, I think that's a more sensible name. It may collide with something down here. Maybe not. Maybe not. Visible fun is just uncompiled fun. Yeah, does that compile? No, it does not. Multiple types have the name uncompiled fun. Indeed, there is this one, perfect, and there is this one, not perfect. So in the mod, yeah, let's not do this. Collect funds, we don't actually, we do that, but in the other, in the other module. this one. Oh, hang on, or is this actually calling that down there? And in the lookup, we have collect all funds. I think that's what we use, yeah. So let's remove this one and this one. Okay. Maybe not. So fun.compile, toast fun, a map of uncompiled functions. Oh yeah, so for every uncompiled function, we also need to track from which module does it come. At least for the local ones. And again, that's, yeah, sure. It has a module and a fun. Okay, yeah. And then in here we need to adjust that. So yeah, the impl will be an uncompiled function.local with a local uncompiled fun, which then contains the module and the actual function. Okay. Here, yeah. Yeah. So we need to set in here. We need to compute a set of visible functions. Strange thing is, we kind of do that, don't we? Like in here, we go over all like modules. Yeah. So let's also store visible in this module. That's just going to be the set of functions. And here we have a map from the module to the set of functions that are visible within that module. Oh man. Yeah. And what we do in here is we go over the definitions. If the definition is a function, yeah, that function is also visible in the current module. So same for imports. Yeah. Okay, then in here, after going through all the definitions, we now have this map of which functions are visible. And then in this overall visible thing, we store that. And then we should be able to just return a tuple. Oh man, this is getting horrible. Of all functions, and for every module, which functions are visible there. this is officially horrible. Oh yeah. In here we have this compilation and the compiled, collect all funds returns some stuff, and it contains the visible functions, and it contains the functions visible per module. Then here we can say that, and that is an uncompiled local function that contains a module and the actual function. And here we can say these are all functions. Well, we can say these are the visible functions that you can see. These are all functions. Please compile yourself. Okay, so compiling round up to power of rec. Before I do that, let me maybe remove some of this, and this, and this, and this, and this, and this, and this. Okay, slowly we're getting somewhere. Okay, compile fun. We have a concrete toast fun. We have a set of visible functions, and we have a map of function to uncompiled functions. Okay, so you know what, let's print the visible ones just to be sure that this makes sense. Oh yeah, we don't need that. Yeah. Okay, so compiling this round up to power of rec function, and we have all these functions visible. The log2 function, ourselves, so we can call ourselves recursively. We have the XOR ins function, we have a pow rec function, and so on and so on and so on, including functions that we import, like for example the plus function for strings. That's pretty cool. Whew. But this is nice. So we've kind of now solved this, resolving of functions, figuring out which functions are in scope, and so on, and kind of broken that down into, now we have a concrete function that we want to compile. And yeah, let's do that. So we know that this is not a built-in function. I don't know how we know that yet. We need to handle built-in functions at some point, but yeah. This returns an egg fun, which makes sense. And the way that works is it and we don't need this because, oh yeah, we do need that. Yeah, let's maybe look at that in a bit more detail. So we create this visible thing. Oh, I see, because these are visible funs. And these are visible variables, basically. So we create a compiler. I think we don't need that. Also, unrelated, I was thinking about creating some like general purpose graph builder, like directed acyclic graphs, and kind of reuse that among many compiler stages, because oftentimes we have something similar. We create this kind of compiler and then we create the body compiler in there. Yeah. Or like SSA builder, single static assignment stuff. Something like that. So then for param, for every parameter of the function, we have a function that contains okay, you know what, let's say we have not just a toast fun, but we have an uncompiled toast fun. And we kind of need the types as well, I'm afraid. Yeah. Maybe also the current module. Not too sure about that. Yeah. Okay. Anyways, we create this thing for visible variables. We create a compiler, we create a body compiler, sure, and then we define visible variables by pushing parameters. Let's maybe do that in 2 steps. you're pushing a parameter. I'm not sure what we get from this. Like, let's just go over the function parameters. And I think it has a name and a type. Which we need to compile using the current module and the types. Yeah, and the module is also something we need. Okay. Yeah. Then we have this body push param. The type gets compiled using that. Okay, yeah. And then we say we take the function body and compile that using the body compiler and the visible variables. Okay, I like that. So here we go. I'm creating this compiler. So let's say, yeah, this doesn't need to know which like definitions are in scope because that's not stored in there. It just needs to return a new one, and that's it. Yeah, on this thing you can create a body compiler, maybe just like that. Yeah, this is not communicated using the compiler, this is communicated as function parameters. On the egg body compiler you can say finish with an egg ID to get an egg body. Okay. Here you get a parameter. And you can push a parameter, returning an egg ID. This looks pretty similar. Can we unify that? Probably can. So let's move the push above the push param, and let's make it so that push param actually just uses push. Oh no, hang on, because this pushes to the expressions and this doesn't. Yeah, okay, that makes sense, I guess. So we have an egg body compiler. An egg body compiler that returns, yeah, for getting something, for getting the type of something, for checking something's comptime, getting the comptime value. Okay. And now we can compile a single expression using the compiler and the visible things, visible variables basically. Okay, let's just check where this fits. So compiling a toast fun needs something. It needs a module. Oh yeah, in here. Yeah, compiling a toast fun needs the current module, which I think incidentally it's fun.module, something like that. And yeah, it needs the visible by module thing. Hang on, like toast fun. Here it is. Module set of string, uncompiled fun, and it also needs the types. Okay, so visible funs is not in scope in compile fun. That is true, but that's fine for now. Yeah, here we just say body compiler. Push param. Oh yeah, that's the result. Oh, that's also do that. That makes sense. Okay, we have a struct. And we compile that value. Instead of to-egging it, which is, I was attempting to say a very weak verb, but it's not really, it's not even a verb, it's just something. So we have a lambda, and we take the type. Oh yeah, we compile that type using our current module. And the types. That's all we need. But that does mean that now we need to add that here. So I think let's add maybe like a compile context or something. I don't know. That just contains stuff like which module are we in, what are the visible things by module, what are the functions, what are the types, basically this stuff. Yeah, and then these these compilers, they can remain simple while we are passing around this context. that should just be the last parameter because it's the least important one. And these compile calls, they need the context now. Well, yeah, not the types, but this one. And it's the module visible by module comes in types. So that in here we can pass the context as an additional thing. Same here, same here, 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 and here. Hang on, where are we? Is this the same code? Still had 2 egg in there. That's kind of... Oh yeah, that was just not updated. Okay, let's see. So here we can say compile that using these. Here we are in this module in this thing. Yeah, this is not like this is called compile. Oh yeah, we don't have functions in scope. Okay, now we're actually at some interesting point. So this is some top level function. It's supposed to be one. So we need to look for a matching function. So I think we just do visible funds is context.visible by module get the functions visible from our module. That's a set of signatures. And then for each of these, what we do is we get the corresponding function. And it will just be context.funds.get signature. And well, we kind of need to... yeah, that has a name and it has parameters. And now we can kind of match those using the logic that we have in the lookup file. We have a signature and we can now match that. So if this signature and this is just a string. I'm not entirely sure how that works, but I want something like this. Basically we want to say we want to match this name and these types, which means giving the arguments. The argument types. Yeah, something like that. And of course we need to handle multiple matches. And no matches like we're doing here. Oh yeah. Okay, so we have some sort of uncompiled fun. Mm-hmm. But we need those signatures and the types. So how do we get the signature? Context.funds. Let me check that out. Egg context has funds, which are uncompiled funds, which were defined in here, I believe. Yeah. I mean, we can easily build a signature from that. So we should be able to do it's weird that signature is both used for strings and for these kind of typed things. Yeah, I don't like that. Okay, yeah, I see. You know what, let's just check if the fun name is not equal to our name, then we just continue. If fun dot, what is it? Oh, we can even do, we expect these to be equal, or if they're not equal, then we continue. And the fun params, which are plum types, we want to be able to match against, now hang on, our concrete argument types. We want to match them against the function parameter types. Or if that doesn't work, then we continue. So, stuff like this. Okay, so this is a string and source. That is true. So this doesn't work because we can use this, like type variable constraints. Match against does not take a mutable one, but just that seems weird. Yeah. Oh no, that does not seem good. even get to that, so meh. And there's a to do here, right? Yeah. Mm-hmm. This one evaluates to an egg ID. Yeah, and here let's just use the first of all cast return value to claimed type. Yeah, but let's just use the claimed return type. So just body dot get returned, and that returns, and then do this down here. Something like that. And this is just return type directly somehow. Yeah. Oh yeah, that's an expression, so actually we want to get the type of that. Ooh. Okay, param types. Hey, try to assign a list of plum type to slice. Yeah, that is true. Okay, here we go. So found matching. And we're compiling round up to power of like. Let's actually look at that function. What is it? Round up to power of here recursive thingy. And what it does is it calls the compare function. And we found a matching function. Int compare, int. Cool. So now we need to kind of compile that function. Yeah. Fair. just have a list of matches, which will be strings. Oh, hang on, which will be matching funds. Yeah. And that will be similar to what we do here, where we have this toast fund substitutions. In our case, though, maybe just a string and substitutions. I don't know. Oh yeah, and substitutions comes from here. Yeah, so we get that. Now we handle multiple and no matches, where we just check if matches is empty, then we do something for the args. Then if matches.len is larger than 1, then we say, hey, this is bad because multiple functions match that. And then for every function, every match, yeah, we have the string and the substitutions. So that's just a string. And B is the substitutions debugged. Yeah, and this is just matches get 0 being the function and the substitutions. Yeah, which we can then unwrap and then do stuff. Not entirely sure. Oh yeah, here we unwrap the name string. Okay, sure. Okay. Okay, this compiles. So compiling round up to power of reg. So we have this to do. We've found a function, a top level function to be precise, and we know the function, we know the substitutions. Now we want to cast those arguments. And we don't need any cast functions here because in the egg we just have casts as explicit operations. So the cast arguments will be egg IDs, I see that, yeah. And then kind of go over the arguments and the the expected parameter types of the function. Which in our case means what exactly? Hang on. We have the substitutions already. Oh yeah, I think we can just do, like, this is the signature. Yeah, so here we can get the actual function. Yeah, that gives us a uncompiled function that has a name and parameter types. So more specifically, it has params, which is a slice of types, and there we can substitute or specialize. Yeah, we can specialize those with the substitutions to get the concrete types that we expect. Okay, so funds is not in scope. Oh, you can only do that for a single plum type. Nope, don't like that. Let's change that. I'm pretty sure we need to do that in, oh yeah, okay, these are defined on maps. But here we do, yeah. So let's do that for slices as well. So you have a slice of plum types and you have substitutions. Well, you should just be able to do this. Specialized is a list of plum types, and then for every of the types we kind of specialize that type using the substitutions, and in the end we just return the specialized substitutions converted to a slice. Okay, and then in here we can just do, you know, this is args.specialize using the substitutions. Pretty cool. We could even do something like this for maps, just to make that a bit more concise. Something like that. Map from string to plum type, boom, returns a map from string to plum type. By creating a specialized map from string to plum type, and then for every entry in the types, and here we put the entry key to the entry value specialized. Like that. And then in here we can just do fields dot specialize with these substitutions, please. And for enums we can just do variance dot specialize for these substitutions. that is clean. Nice. Yeah. This is struct. Like this, I guess. Oh yeah, if is comptime, that argument, then we just cast that. Oh no, then we just have a value, you got comptime. Yeah. Amazing, of that same value with a different type, and that's possible because values are not really typed. 3, 2, 1. What is going on here? Value is not in scope. Oh yeah, this is body get comptime. Oh, no, this is just a cast of that argument. And that doesn't work because this needs a type, but also a source. Yeah. Expected archetypes. Let's pull this out. Yeah. Nice. Yeah. And this needs a source, which will be the name source. What is going on here? Push egg body compiler and egg ID, but it needs an expression. Because it's already been pushed up here. Yeah, no, let's not do that. Wait, hang on. look for a matching function. Fair enough. So then we cast the arguments, which is fair enough, I think. Let's just store this as the kind. Yeah. I like that. Okay, compiling round up to power of rec. So we have a to-do somewhere. Maybe here. Is that the to-do we're hitting? Probably. Yeah. Okay. So what needs to happen next? We want to see, are they all compile time known? Yeah, we kind of need to yeah, not sure how to deal with that. Yeah, I'm just gonna do this for now. Okay, hang on, we have the return value, right? I think we do. Yeah, here we just put the fun dot hang on, with the yogurt call, that I think that just needs the signature and the arguments. Okay, try to assign slice of egg ID. Oh yeah, this is not supposed to be a yogurt call. Should be an egg call. Yeah, no. And the egg call, let's change that so that it just stores a string, and that's it. Yeah. So figuring out the return type. I don't know how that works, to be honest. We have some sort of function. Function has params. Yeah, return type is fun. Dot return type dot specialize using those substitutions. Simple enough. But return type is not a field on there. That is should be. place where we construct uncompiled funs, we also need to figure out the return type. Oh, hang on, we can't do that for imported functions yet. Yeah, that is very fair. So let's not do this actually. But instead, let's say we're looking for the concrete we have some sort of uncompiled function. And basically what we want to do is we want to have some sort of compiled fun. I think we want to follow that function to its definition if it's an imported function. So basically we want a loop, and if the function if that is a toast function, then we want to break with that toast function. Otherwise, we want to say function equals I think we want to switch on that input. It's a toast function, then we want to break with that. If it's an imported thing, then we actually want to say function is context.finds.getSignature. So we want to follow that import. So if we use, I don't know, the plus function from the standard library, we say, oh, that's an imported function, so let's look into the standard library. There it is defined as an imported function from the int module, so let's look there until we finally reach the toast function, the underlying actual source code of that function. And once we have that, we can then do stuff. So we can say we have this toast fun that has return type that we want to specialize. Man. Okay, toast is not, local is a thing. Local fun. And let's actually break with the module as well. Oh no, just with the fun. Yeah, that's fun. That's fine. And because this is not actually a toast fun, which is weird. This is like a local fun. And that has the toast. But it also has a module, which I think we need to specialize the just visualizing on what's going on here. Oh, there's a then. Doesn't make any sense. Don't have it imported. Does break not take? Oh, I see. I think break takes things like this arguments. Yeah, that's cool. So toast.return.toast is not a field on local uncompiled fun. yeah, it's called this. So this is a toast fun. Yeah, and the return type needs to be compiled using the module that the function is in, which is local fun.module, and the types. Oh man. So we compile that and then we specialize that. That's crazy. So yeah, types is not in scope. I might go on a walk. Well, context or types probably. Oh, yeah. Okay. Yeah, return type is now just a variable that we have. And the builder is not in scope because that is the body, I believe. Yeah. So 130 call.function.b. Oh, printing egg. Okay, that's fine. I'm totally fine with that. Where's that? Here. Oh yeah, this is just the name. Sure. Oh my god, that is actually pretty cool. That is super cool. So we renamed the less than function into the actual less than operator. And there were some places in the code where that was not updated. Now that gets discovered by the compiler. That is super cool. Hang on, format and it. Yeah. Let's use the less than function. That's clean. Amazing. Okay, so there is no matching function named item for this args theme. Oh yeah. That is part of the, functions and struct access is the same thing kind of stuff. Where I have some sort of to-do in here. Yeah. So basically if the argument types, if there is only one argument type, and the type is a struct with fields, and one of the fields is named like the thing we're going to call, then the expression, whatever that is, I think we just want to return that. ID error. Yeah, I think we want to do this and then return OK. Just some egg expression kind member. of that is, well, this one. Oh yeah, extend one little. Important. Nice. Yeah, comptime should be handled specially here. An egg expression kind dot member of an egg member of the argument, this name. Yeah, the type is the first field's type. Yeah, okay. Should work. Oh yeah, it has a function which is, I think this needs to be moved further down. So if this is a name that we're calling, if this is like a complicated expression in and of itself, then that's probably a lambda call. But if it is a function call of some name, here's where we want to do that, I think. Let me think about the priorities. If it's a name, even though there's, even if there's a variable with that same name in scope, we don't treat this as a lambda call of that and interpret that as a lambda, but instead we first we check is this a struct access, then we check is this a local variable in this function, and if none of that is true, then it's a top level function. Okay, so name is not a field on toast call. 263. Yeah, this should just be the name, I believe, like that. Hang on, if that is the struct field. Oh, that evaluates an egg ID. Oh no, we want to return immediately. Amazing, switched on non. Ah yeah, node.item. This now gets parsed correctly. That's pretty amazing. And node.rest, we switch on that. Not quite, I think. Oh, and some of the functions actually get compiled already. That is amazing. That is seriously amazing. I'll just try to put parentheses around that, see if that helps. If yes, then that's a parsing issue. If not, then that is a deeper error, you know. Line 58, that's down here. Sorry. Like this. I'm curious, does that? No, still same thing. Oh, okay, so I think the struct access, even though that gets kind of resolved, it doesn't get... Oh yeah, look at this. We don't want this to evaluate to the struct type, but to the field type. So that's kind of So field type equals, this is the struct type, and from that we get the field, giving us the field type. Okay, extend one level, that is correct. Now we know that this is a struct which will unwrap. Okay, giving us the fields, which is a map from string to something, so that, yeah, should work. Okay, yeah, we can now switch on that. Slowly, you know, creeping forward in this source code. Okay, so there is no function named plus for the args string and string in the playground. That may actually be the case if we don't import the plus function. Yeah, we import the plus function for integers, but not for strings. Oh, that is cool. That is super cool. So let's import the one for strings as well, so we can use that. We now have proper like modules and scoping and stuff. Okay, yeah, built-ins, we need to handle them. But I think before I do that, the weather is so good. I'm taking a walk and then continue programming then, maybe. Let's see. Alright, fixing built-ins. Let's maybe look at how they should work. Or like where that's coming from. We have this compile thing, and we try to get an uncompiled function. That's probably here. Compile a function, then compile an expression, and then we see we have some sort of call. Yeah, meaning that we'll oops. Man, that we have some sort of function name. So what we do is we try to get the function. I think I should maybe do stuff like this. I know, these are the visible functions that always exists. Yeah. And visible functions includes the built-in, you know, built-in stop model int function. Yeah, I think this is the one that's failing. Okay, so that's not it. Okay, so where else do we have get function? Here we do that. Context.funds.get of some signature, the signature coming from this block right here. So the signature being the you know, the first thing of these matches which get built up here, which is this signature. But then shouldn't this have already failed? I don't quite get that, to be honest. Here we push something into the matches. Well, let's maybe print that. Okay, so we are compiling the times function, and we do found a match. So in there's a call to the mulins function as int. Oh, I see. Okay, so this is guaranteed to work, sure. But then this one fails. So for imported functions, it may be that that function doesn't even exist. And also we need to make sure that the function is being exported. It's kind of important. Context.funds.get maybe. Yeah. And this is not an error of the int module, but of the fact, like how built-ins are handled, basically. Because the context funds, they only contain uncompiled functions, and these are defined somewhere, I think in the lookup. Yeah, where they are either a local uncompiled function or a string. I think maybe we should just say raw builtin in here. Maybe that would actually already be enough. And then in here, when resolving these, down somewhere down here, nope, down here, yeah, we also handle built-ins. Either we do it like this, or we just add built-in functions to that giant map as well. That would also work. Yeah, I think that's more elegant. Rather than adding built-ins here, let's just say that we add built-ins in here. We have this map of egg funds. Well, let's just say compile all funds containing the funds, yeah, and then basically for every built-in function we basically add them to this map as well. And we can even put that in collect all funds, which I believe is also here. Maybe not. Yeah, we just want to call this collect all funds. Yeah. So we want to create a built-in fund. Yeah. That's not quite correct, I believe. Not just because of the error, but also because I believe that they also need the parameter types in the function signature. Oh yeah, this is an uncompiled fun that is expected there. So that's maybe put in something like this. Something like this. I accept like uncompiled fun impl. Yes. Oh, here we are again. Either an enum or imported. I see. So basically we want to yeah, I think we want to have a separate case for that. Which, yeah, okay. Fair enough. Like everything's pushing me towards that, so I'm just gonna do that. However, I want to I think I don't want to dig too much into the implementation of the uncompiled function to get the return type. So while this is fine, I believe, I think this should be built in first of all. And I think I'll add a return value in here, so that later on in compile fun, which is somewhere here. Oh yeah, I see. What do we use local fun for? just to get the return type, and that's basically it. Yeah, okay. So let's do it like this, maybe. So we calculate a return type, and for local funds, that's just the local fund return type. For imported funds, that is the well, we get the function, and we continue looping, and then there is built-in, where we basically do built-in the signature return type, something like that. True. So in here, in line 15, previous cases to nothing, really. Oh yeah, because we want to break with that return type. Done looping. Okay. Yeah. For the imported function, I think we'll actually need to and make sure that the function exists. No, we already do that. But kind of attribute the error to the import instead of the call side. Basically, where you say import built-ins dot mul ints int, there's where we want to show the error. But actually, though, I think this is totally fine. We just need to kind of change how functions are created in here. Yeah, so for the built-in functions, we need to add the param types as well. So we need to build some sort of signature using, let's say, a string builder. And what we do is we first print this part. And then for every param and param types, we basically print a space and then the param. Yeah, and that's going to be the signature. So now the mul ints function should be found. Look at that. That is beautiful. And this is actually a useful error. Like, this is just plain wrong code. From the built-ins module, we also want to import the concat strings function that takes 2 strings, so that we can then use that here. We're getting useful errors. Wow, so I think we need to import the equals function into the list module, which makes a lot of sense. Okay, so what do we have here? We have a list. It's either empty or it's more, and if it's more, then we have this node. And here we say that there is no matching function named item for the args. Boom. Just one argument, which is an enum of either sum hang on, what? Oh, I see. So this has a stronger binding than the dot. It sees it as this right here, an enum that's always sum containing that with a dot. Okay, so let's parse that differently, maybe to toast. Somewhere we do like parse suffix dot. Yeah, questions, where is that used? In here. In parse expression, that is true, but it's also an undotted expression. Hang on, parse undotted expression. That is true, but it also parses structs and enums. I think we don't want to allow that, like especially parse struct and parse enum. I think if you have something like this in your code, intuitively, like this is a call, and we have a struct that then contains that thing. It's not like we have a struct containing x being foo, and then we call that struct with bar. Oh, but on the other hand, oh man, this right here is just a call. Yeah, same thing. We don't want to pass that inside this ampersand, but we do want to pass that for this type in here. So parse atom is something that doesn't contain a space. Yeah. And then we have this undotted expression, which may be, like a more complicated thing. But we don't want to allow these structs or enums at this point. Instead, I think we want to allow them here. So we try to parse a struct. So the in parse struct. What we do is we have this colon. Oh, hang on, no, this is only if we have multiple children. Yeah, parsing an entire bacon. We do have a different parse struct as well, don't we? Somewhere here. So here, after the colon, we only accept atoms. So nothing containing white space. If you want to put something in a struct that contains white space, you gotta put parentheses around that. That is a fair take, I think. But then again, we do want to allow dots in there. So basically dots are more binding than normal calls. That's the thing I'm kind of struggling with here. So let's go back to this parse expression thing. What we don't want to do is first parse undotted expressions. I'm actually not sure about that. Let's go the... I'm really not sure about that. In this case, yeah, it makes sense to pass that dot. But what about this? Like these dots shouldn't be treated differently, I think. Oh man, okay, so this becomes difficult. Maybe they should be treated differently. And this should be allowed, but instead here we would require parentheses, which would also make sense, by the way. Like that. Yeah, okay, so I think we'll actually need two versions of parsing these, parsing suffix dots, basically. Yeah, we'll have parse expression. I do see that that is kind of confusing though. Okay, you know what, let's merge parse expression. Like these, you know, parse undotted expression, parse expression, parse atom, parse suffix dot. Maybe we can merge them into one parse expression thing that accepts a parser, but also can allow white space, which is equal, and allow dots, which is also a bool. And I think we actually want all of these, we want to support all of these combinations, basically. We have places where we want to support white space, but not dots. As in, you know, we have some expression, then we find a dot, and now we want to parse something that contains white space, possibly, but no dots. Like a call, for example. Yeah. This right here is a place where we want to allow dots, but not white space. There were cases where we want to allow neither, like when parsing this left part right here. And there are places where we want to allow both. For example, just as like a top level expression. Something like this. Okay, so let's do that. Yeah, and rather than doing like parse undotted expression, which then calls these things, we're just going to inline that in here. And rather than parse atom, we'll just do that. So we try to pass some parenthesized expression. Boom. Some int, a string, a name. These are all self-contained expressions. If none of that matches, we're down here. Oh, actually, no, we're not. We may want if we allow white space, then we'll also do this. Parsing structs or parsing enums. Yeah, that means we basically don't need to do this anymore. And then there are basically two things. If we allow white space, then we want to parse arguments by saying, hey, please parse another expression here, but this time inside this call don't allow white space, but do allow dots maybe, or pass our allow dots on. Hang on, what was the case where we allowed white space but not dots? We're on the left side of a dot. Yeah, there we may have some sort of call. But not allow any form of dot. Okay. Otherwise, if we allow dots, then we try to pass the suffix dot. Which just does this, so yeah. And here we loop, so let's maybe inline that. Yeah, and rather than this, we just break, do the inline here, and we assign the result to the parsed expression. Oh yeah, and rather than undotted, we just do parse expression where we allow white space, but we don't allow dots. Oh, hang on, and we don't always allow white space. We allow white space if we are allowed white space. If you're only supposed to, if you're inside a struct and you do x colon, then this is a place where we allow dots, but there can't be any white space afterwards. Yeah. Okay, and then if we allow white space, then we also may parse a trailing equals sign. Yeah, I think this is nice. So rather than having all these tiny specialized weird methods that call each other, we just have one method that tries to parse like simple fundamental stuff. Then stuff that's a bit more complicated. And then depending on whether white space or dots are allowed, it tries to parse several suffixes, including calls and dots and equal signs. That is clean. Yeah, okay, so several places will probably not work now. Yeah, because this parse expression now expects several stuff. So the body okay, so we will have a single line expression, single line definition. What we want to do is to parse an expression where we allow white spaces and dots. And then in here, let me just look for that directly. Yeah, so in the parenthesized expression, we allow white spaces and dots. Everything, all restrictions are lifted. On the right side of an equal sign, we allow white spaces and dots, I believe. I think this also requires allowing dots, actually. Yeah, I'm not entirely sure about that. We can always restrict that less later on. Okay, so we have no children here, and oh yeah, we have a struct. Then we parse an expression. Parse struct. And the line is only ampersand. Okay, so in this line right here, we only have a single child, I believe. Like parse, so everything should be allowed here. Yeah. Then in here we have an inner variant, and again everything should be allowed here. In here we have only a single child, which is where we also want to allow everything, as in everything. Oh, and that's actually like a bacon. Yeah, so we don't need those. For the bacon, it's obvious that it allows spaces and dots because it's separated using indentation. For lambdas, we have an equal sign, and afterwards we want to allow anything. Okay, for the switch, we have cases, an arrow, and after the arrow there can be anything. Then we have an expression. of the bacon. We want to allow everything there. Parse dot. What do we do here? So we have the bacon. Oh yeah, we have a bacon with, you know, like a new line and then dot something. Then the thing on the right, we basically want to allow everything there as well. If we parse a slice of bacon as expression, oh, this is not the parser level. Yeah, okay, so parse atom exists in some places. I want to replace that with parse expression. Yeah, but no white space allowed, but we do want to allow dots in that case. Same here, well, no white space, but we do want to allow dots. Yeah. Oh. Yeah, this is an entire bacon, so there's no need to specify that we support everything. This seems to compile at least. Okay, okay, that is pretty cool. Not quite. So no matching function named negate for the argument's string. What I suppose happens is that negate gets applied to this thing, which is actually, I think, the same take here, like negate of something. Yeah, no, hang on, for the, yeah, we can fix that. I think for calls, aka this, we don't want to allow dots in them for the arguments. Yeah, that makes sense. Nice. Okay, so this is more of a, this is an actual error in the code, so this is always nice, being shown where you are wrong. In particular that we don't import the minus function for integers. And there's this one. And that is, oh. When I started this video, I was like, let's write some code that currently compiles, but that should not compile. And I wrote this piece of code, where we call this bar function with an integer. And bar is, it says I accept any t, and then I call foo. And what we didn't want to happen is that the bar gets compiled for integers, so it looks for, you know, so t is an integer, it gets just compiled for that, and then it looks for the foo function accepting an integer matching this one. This is what we didn't want. We wanted this to be an error, because that, like, this function should work for any t. Now it actually doesn't compile, but instead it tells you, well, there is no matching function named foo. That's exactly right. Okay, so I'll remove this. That is nice. That is really nice. Let's make something more reasonable here, like creating a list of length 2, maybe or length A, and then taking the sum of that list. Man, that is cool. That is cool. Probably not in scope, I guess. Oh hell yeah. Yeah, I can already see that. So we have a maybe, but we don't have the unwrap method. We want to import unwrap that works on maybe t and string. Now, I hope, now it should compile that string is not in scope. Oh, that is amazing. You actually get same error handling behavior. And you need to import things to use them. Like, this feels different. This feels even different from matinees, you know. In matinees, like, things, if you comment out some code and it's not used, then it's not analyzed. It's not even type checked. Code's only type checked for concrete types. This feels a lot more robust. You know, that you have to import stuff and code is checked regardless of whether it's used or not. Yeah, that is just nice. Yeah, so here we want to import the crash function, taking a string. I mean, look at that. Look at that. Oh, that is really true. May. Yeah, this is supposed to be parsed as this, as first increment the node and then dot rest. But we don't want this, we want this to happen. So we need to put parentheses on. That's exactly right. Amazing. Honestly amazing. Oh yeah, so types and type info, like this is kind of, I think I'm gonna remove this. Just because the comptime functions, they are not really, I don't really have a plan for them right now. I do have a rough plan on how to support them, but, well. Okay. So we're back in to-do land, into egg. Something to egg here, and we have some sort of to-do implement. That is completely right. So we have the compiled functions. Hang on, is that it? I think that's it. It is supposed to return an egg, and I think the egg just has a list of compiled egg functions. Yeah, it does. Like this. As well as the entry module, which we also have. Yeah, funds equals compiled funds. Cool. Clean. Okay, what's going on here? This takes an egg signature. Yeah, no, that's simplified things. Egg signature shouldn't be a thing, you know. Nope. Just I meant from string. From strings to functions. We compile the entire egg. The entire toast to egg, and now like, we have resolved types in here. I think every one of these expressions has a type. Let me make that sure. I thought we printed that actually. So we write egg expressions. Oh yeah, but we don't actually write their ID. But we could. We could say every one of these expressions has a type. Damn. Each of these is an integer. Function calls are already resolved in here. That's crazy. That is indeed crazy. And sure, these functions, they are not yet monomorphized. You know, the maybe unwrap function just calls the maybe unwrap function taking a string on, you know, maybe t, not yet specialized to concrete types, but every function is now bound to a concrete other function. Even in generic functions. That is sane behavior. That is really sane. And we can really see that this is like a string, sure, this is a cast, sure, of that type, of this type, to that, which is the same type, but sure. And here we have another comptime string, because of course we do, and we call this unwrap function. I mean, what more can I say? Like, this is pretty amazing. I'm just gonna, you know, look through this code and see if there are like major issues I realize, or if there's. But so far, like, this seems perfect. Oh, this is a function that's a bit more difficult. So what do we do here? We add the first input. We add 1. Okay. Yeah. We cast that to an int. We cast that to an int again. So we multiply those. So we add 1 and compile that to itself. We check if that is greater than the recursive thing here. Then I believe that's the square root, or that's the original input or something. Yeah, I think this is the candidate and this is the square root we want to reach. If our candidate, if we would add 1 to that and then square that, aka multiply it with itself, and the result of that is greater than the target value we want to have, then that is already the square root and we're done. So if that is equal or greater, boom, we're ready, we're done. And if it's equal, then then we return that plus 1. Oh yeah, makes sense. Otherwise we're going to return the smaller one if that is too big. And if it's less, then we try to call ourselves recursively, with a new payload being the incremented candidate, and this one being just the target that we had before. Like, this seems like sane code, apart from, you know, all the casts from int to int and stuff like that. But yeah, I like that. I really like that. Wow. Yeah, let's do something nice. Let's say what is this? Oh, this is, let's go through this, I think. I think this will be interesting, incrementing a list of numbers. So we have a list of integers being a recursive type starting 2 types up, so that would be 1, 2 starting at this enum. Makes sense. Seems correct. And this right here is also a list. Okay, so we have some list. We switch on that list. If that list is empty, then we create an empty struct. We create the empty variant. Oh, and there should be a colon afterwards. So just in here for the enum variant, there should be a colon. And then we cast that into this one. Perfect. Into empty with nothing. Like, here is no colon, so empty has no payload basically. Cool. Then what do we do? Oh, we return that. Makes sense. In the more case, we kind of this is the payload of this enum. What we do is we extract and the payload, because this is the more case, it's actually this right here. So it's a struct containing the rest and the item. So what we do is we extract the item. And we have this comptime 1. Sure, we cast that item, which is an integer, to an integer. We have another comptime 1, I guess. And then we add our integer from the list and 1. So this is the integer incremented by 1. And then we get the rest from the list, giving us the rest of the list. Makes sense. We cast that to the same type that it already is, sure, and then we call ourselves recursively with that. So incrementing the rest of the list. And finally we build the payload for the list, which will be a struct containing the new rest, which is the result of calling ourselves recursively, and the incremented item. And then we create an enum more with that struct here as a payload. Yeah, and then we cast that to this bigger type, and we return that. That is perfect. That is honestly perfect. Crazy. String is cast. What's going on there? Yeah, this is pretty crazy code. Okay. Form digit. Yeah, fair. That is maybe kind of cursed. I don't know. Okay. Yeah. Cool. Yeah. What else? Round up to power of. Calls power of recursive thing with something. Sure. Hang on. This calls a workspace call int subints. Does that exist? Not really, right? Not really, I think. Rather, we have some built-in functions. So here. Where are the built-in functions? Come to think of it. Huh, I don't know. Oh. Let's look in here. We have the compiled functions. Oh yeah, we only do something if this is a local function. Well. I think we should switch on that. If it's a local function, then sure, do something. If it's a built-in, do something else. You know, compile a built-in, basically. Otherwise, the imported ones, they can just be skipped. Oh yeah, this is where we do the spiel of the... Oh, where was that? Compile fun, maybe? Down here, like this compile built-in... Nope. Hang on, at some point, what was in the lookup? Yeah, we create the built-in funds. Let's do that. Yeah. Cool. That's very nice. So now at some point there should be built-in functions in here as well. Yeah, here. Beautiful. And actually these in here, they should call the built-in fun. So I think in compile fun, where we call a function, we actually need to handle, we have some sort of match with a signature. Yeah. Oh, and now we have some imported signature. So what we do is we should also reassign the signature. Like that. Yeah, the substitutions also need to be updated somehow. Well, okay. So now the now the int equals function just calls the built-ins compare ends function. That makes sense. Beautiful. Yeah, nice. Now the rest of the compiler pipeline, meaning mostly this part right here, converting the egg to yogurt. That's going to change significantly. because the egg is now completely different. I do need to worry about like compile time evaluating functions. We don't do that yet in the egg. Hang on, we do that, don't we? I think we do. Yeah. Because in here we don't need to do this anymore. We don't need to do this. Like, this part got way simpler. Way simpler. Two yogurt of egg. Not entirely sure about that. Oh yeah, some of that console printing is gonna, like, a lot of this code is gonna find its way over into this compiler stage. For example, running code at compile time. Yeah, like this will be way simpler. Lambdas and stuff like that. And we don't need to figure out like which variables are captured, stuff like that. No, just at least not immediately. Okay, you know what, in the main file, I think I'm actually gonna still comment this out and instead look at a function that is supposed to be completely compile time evaluated. Like, make a list of two numbers and then sum them up. That should entirely happen at compile time. Currently it doesn't though. For example, haven't found the main function, which is kind of concerning, but I may have just overlooked that. Okay, test playground. I'm just looking for some test playground stuff. Main function. Okay, so we created two. We call this function. Not sure about that. So we do like call make list. With a comptime 2. At this point in time, we should just do that. Like we should just run the function instead of compiling it, because we know that it's like all parameters are comptime now. You know what, to get in the mood of comptime stuff, I'm just gonna do this first, which is way simpler, hopefully. Which is just that if we have some sort of position, let's say with a x and y, and then we return post.x, that should not be compiled into a runtime struct access, that should just return 3 directly. So where's the main function? Here it is, here it is. Yeah, so this is still a runtime access, and instead there should be comptime. Let's do that. So what we do is we, well, basically we check if the field hang on, what do we check? We check if the not too sure about that. If the struct itself is comptime now, basically. So we get the struct. If the struct is comptime, then this is just that. It's a comptime value. Oh, okay. The kind depends on whether that's comptime or not. Yeah, and it's just an expression kind. Dot comptime of body get comptime of that struct. That's the value. Yeah, we know that value is a struct, so we can unwrap it and get the field value. Yeah, like that. Otherwise, we do this. We get the member of the struct with that name. Amazing. And then we have the field type, which is just that, either that or just body type of struct, which I think is even more clear. Okay, yeah, I like that. I really do like that. So now the main function should just return 3 directly. How is it that the main function ends up at different places? Does it even? Or did I just overlook that? Yeah, it seems like it does. Here's the main function. Oh yeah. Amazing. Just returns comptime 2. That is pretty cool. Okay. Right. So where's that not working? Let's maybe do this down here. We check if all arguments are comptime known. Should run at comptime, maybe. That's initially true, that's our assumption, and then we go over the arguments and we check if it is not comptime. If one argument is not comptime, then it should not run at compile time. And an exception to that, if the name is this builtin type of T, I don't know, like this is weird, you see, then should run at comptime is just overridden to be true. So we should do something like this. Okay, so if it should run at comptime, then we get the values, which will just be egg values. And basically for every value we do get comptime of that argument. Nice. And then the result is function.run argvalues. That's pretty great. Yeah, we'll need to deal with circular calls, etc. Yeah, and we switch on the result. If it returns some value, then this is just a yogurt, so an egg expression kind.comptime of that value. If it is a crash, then this is, well, body.push egg expression kind.comptime egg value.string. And we return an egg expression kind dot maybe builtin. Egg builtin, maybe. What's crash.b? Not too sure about that, but meh. Okay, and if it's a comptime error, then we just immediately abort, returning an error of that message and of our name. Else, if we should not run it compile time, then we'll just actually call the function. Okay, that's pretty cool. Yeah, so running a function. This is run fun. I'm not sure about this. This one, like runtime crash returns plumb type for some reason. That's weird. Let's maybe not do that. You know, just like that. Yeah, and then hang on. Yeah, we'll figure that out. Yeah, compiler is, I don't know. So we are trying to run some function with egg values. Okay, so I do see that we need some sort of compiler to protect from running infinitely. Maybe compile stack.mum, I don't know. Because this compiler really is just a stack thing. Something that maintains a stack of compiling or running functions. Yeah, something like this. Egg stack, I don't know. It doesn't really have this. Nope. Okay, yeah, so what you can do is you can compare these entries. I mean, sure, why not? You can start running something and start compiling something. That makes sense. And then we'll also, oh yeah, we can also print that stuff. That entire printing stuff, updating stuff. We can move that in here in its own little separate file. Clean, honestly. Yeah, this is not really the compiler, but let's call it stack. And let's maybe call this entries. And have some sort of explaining comment, because that makes sense. The compiler stack because plum interleaves compile time running of functions with compiling functions. We need to ensure that function compile time execution is not recursive. So we maintain a stack of the compiler itself, keeping track of the currently running and compiling of the functions that are currently running or compiling. I like that. Okay. Yeah, this seems pretty clear, I think. Yeah, this should all just be that. Signatures are just strings, I like that. So we have start running. Done running is currently running. Amazing. we can print the status. Amazing. Okay. Yeah. Terminal output to give somewhat the progress with arbitrary part-time code execution. The compilation can take some time to give feedback about the progress. We print stuff to the console. Yeah, and then we have this. I think this opening bracket is actually part of the escape sequence, like part of the thing that always has to be there. So I think I'm gonna put that in there actually, and just not have that everywhere, like in here. And put that on the same line, on a new line. Yeah. Amazing, we have an egg stack. Is that actually like mutated at some point? No, it's not. So that's not user reference here when we don't need one. Oh, and I will also immediately return. Okay. Sure. Nice. And this was too standard error. Okay, but this, I like that this is kind of a self-contained thing now. So running a function would now require an egg stack. And then we just check stack dot stuff. Yeah, I like that. In this case though, I think it should just return a comptime error. Nice. Then in here we switch on the toast fun body, maybe. I don't know, we actually don't need that. We can just, because built-ins, they constant fold, I think, and they are just normal functions. I think they should be at least. So yeah, I think this is just always code basically. Match.fun. And we don't need this. Yeah, so here we have an egg. What was a code builder or something? I'm actually not sure, but this is kind of weird. Egg code compiler or something? Yeah, egg code compiler. Sure. And then we have the body compiler within that. Something like that. Okay, so basically for every hang on, we have match.fun, I think. The function has params. Oops. That should be pretty similar to the setup when we compile a function, shouldn't it? Like this one. Here, push an egg body compiler. Where do we do that? Yeah, this one. This general, like, you know, this sort of stuff. I think that is pretty much what we need here. So we also create a map of visible things. Yeah, this is probably still a good idea. We build a compiler, yeah, which is an egg code compiler. We build a body compiler. We see what are the parameter types, which will be the match fun parameters. And then we say, well, the type is this. But it should also be specialized using the match, what was it? Like match substitutions. Then we push not a parameter, but instead what we do is we zip this with the actual values, the outs. So we do add expression kind or comptime of that value. That's going to be an expression of the item A. And the source here, I'm sure I use that as the source and use this as the type. Then we say, please compile this function. No, we don't really need the types here. Yeah, no. Yeah, we just say compile the body, compile this function body using the body builder with these visible ones, and this is the context. Which we which is an egg context, which we have in here, right? No, we don't actually. Oh, but we do in here. So within here we have an egg context. Okay, so let's just pass the egg context as a separate thing in there. So should the egg context contain the stack? I think so, actually. Okay, yeah, so we finished that. That is the returned value. Yeah, we need to cast that to the claimed type. We still need to do that, yeah. But we can just say this is the egg value. We can just return that. That's pretty nice. Like that. And we don't even need to do all of this. Oh yeah, if this is an error, then we return the error message. That makes sense. This will just be the context. Yeah. Sure. It still is a bit messy, but it is a lot better than before, I think. Yeah. And I think this is actually something that that just doesn't need to happen. Like, I think this needs, there should be like a general thing for built-ins. You know, if we have some sort of built-in and we compile that, something like this. I'm not entirely sure about this, but yeah, it's gonna work out for sure. Yeah, so this is an uncompiled fun. I'm just wondering how comptime stuff and function overloading really interact with each other. Because if we have something like, parse JSON comptime, I don't know, of, this one, and then we do distance of a value, or like this is some point, using the distance function that between one point and another point, maybe. And origin is defined as point at 0, 0. The point being, oh no, the point being, I want some way to support this kind of thing. No, hang on. Yeah, the squared thing. Something like this. Or written in an alternative way, a dot x minus b dot x power 2. Or just square. Like, assume you have this in your code. You take the square root of the sum of the difference between a and b. Actually, I like the prefix notation a bit more in this case. Like that. Well, something like that. Whatever, you have some, the point being you have some distance function between points. Should that work? This one right here. And if that is not difficult enough, like, I think this should work. This is just a function call with a comptime string, so this should be guaranteed to happen at compile time, giving us some type, I don't know, x is int, y is int, something like that. And then we should just be able to use that, use function overloading to call functions defined with that. But what if we have something like foo that takes a JSON string and it returns something like, I don't know, int maybe. And what it does is pretty much the same. Like this. This function, you should only be able to call that at compile time. That is not communicated in the signature at all currently, which makes sense because does it though? Because the content of a function may depend on whether that function is may depend on the comptimeness of these values. Yeah. But then again, how would this function even look? We would need some sort of built-in function, actually, some sort of in the built-in, you know, in the built-in module there should be some function like create struct or something that just takes a oh yeah, in the built-in module there should be some sort of value being defined as either a struct, and then it contains like a map from string to other values, or you know, an int or an enum with actually a struct, yeah, with a name and a value. I believe that's it. Like, yeah, some other, like the fundamental types, they should be in here. But basically a representation of types where we have just maps of strings as structs. Basically kind of similar to like JSON encoding maybe. Not really JSON, you know, it's not, has nothing to do with JavaScript, has nothing to do with notation even. It's just basically a first class uniform value representation of all, like you can represent all values as this. And I think then we want some sort of create function maybe that takes a value and then it returns something, we don't know what, and there is a built-in function. I think something like that makes sense. And then we could call that function within this parse JSON comptime function. Yeah. Then we can just call this create function, giving us some value. The question is, how do we even, we can't even write the signature of this function. We can't even, and for that matter, the signature of the parse JSON comptime function, because that will take some JSON string and return something. And we don't know what. Maybe I'll actually allow a question mark in there, you know, like something like comptime or something to indicate, you know, this function can only be called at comptime. Maybe worth it. I don't know. And well, Well, then the question is, how do you, like, these functions, they can't get type checked for obvious reasons, because parts of these values inside of them, they will be only compile time, only known for the concrete values that you pass in here. Yeah, for instance, even this function would have to have some sort of question mark operator in there, I think. Maybe. Oh, or rather, you kind of have to annotate that. Yeah, currently you can't annotate functions, but maybe you'll have to annotate functions like this. And then that you can check this function in isolation. You know what type pointers. So you can just call functions with it. Yeah, okay. I think that is actually fair. But now the question is, what happens if we don't do this? You know, if we do this. I think this code should actually not compile. If you have some expression where the type is only like where the type depends on parameters of that function, you just cannot call functions. You can't pass that type into functions. I think that is fair. Yeah. So this wouldn't work. The question is, should we allow something like this? I mean, you know, this parse.json function would probably take, you know, call parse.json. Something like that. We have a JSON string, we call parse.json on that, we get back some JSON object that is actually a JSON which is an enum. Similar to this, it doesn't have enums, you know, it's like the typical JSON thing, it has null inside, stuff like that. And I think then there's probably some sort of toValue maybe defined on JSON, we could do that. And then we can do create on that value. We don't need to do anything with that returned value. Yeah, I think that makes sense. I think that does make sense. Ooh. Which means that every function can be type checked in isolation, even if some expressions within that function, like this expression here, don't yet have runtime known types. Even if they don't have statically known types yet, the type of this here is unknown. Yeah, I think I like that. I think I like that. So actually in the egg I don't need to do compile time evaluation yet. That's the cool part. What? I don't need to do compile time evaluation yet. Period. Yeah. Oh, hang on. I do. I do. For the cases like this, for like, you know, we have parse JSON comptime of this. Like, what is the type of that? We don't know. Unless we comptime evaluate that. Oh yeah, like, okay, this function here shouldn't compile. But this function should compile, even without this. So in this main function, we should comptime evaluate this call. And we need to do that before the egg, so that the type of point is known at compile time, so that we can then resolve the distance function. Yeah. Okay. Enough. Daydreaming or something about comptime stuff. Okay. I am wondering though, like, we can compile parse JSON comptime in isolation. We don't need to say run this function for this input directly. We can say, you know, please just type check this function. And that would give us some sort of egg for the function that we can then later on, then we can still evaluate that. That's totally fine. I'm not sure what to do. Yeah, I don't know. Maybe that was a stupid idea. I think I'll just go through this. So we have an uncompiled function that we want to run for some concrete values. That is not enough information. That is the call down here. We have here some sort of function. Find the function name. Yeah, okay, that is a lot of stuff. This is a top level function. Sure. Boom, we have these. So if the function should be called at runtime. That is an uncompiled function. Hang on, let me go through that. Let me rethink what is an uncompiled function. It's a function that has a name, makes sense. It has params. Which is it's nice of plum types. And it has uncompiled fun impl, which can be something. Okay, so we actually need to run that uncompiled fun, yeah, sure. And also the substitutions, put them in there, maybe. Yeah, expected archetypes. These are... Where are those coming from? Oh, here. Yeah, okay, these are just the function parameters. Okay, so I think for run function, we want some sort of uncompiled fun. Yeah. The substitutions. Then we have the concrete values. Something like that. Yeah. So we can then calculate the expected argument types. Now these are just the argument types, period. Which is the fun. Oh, okay. Fun params specialize with these substitutions. We build the signature, which will just be the module dot and then fun, the function name, and then for every... Oh, I feel like I've done this a couple times now. Oh man. Not super elegant, I guess. And for every arg in archetypes, do b, just add that there. Okay, and then we have the argument types. So we have, yeah, I guess the args and the archetypes. Simple. Yeah, we don't need to do this. Like, these are just param types. Pretty amazing. So we'll just take egg expression kind comptime of the value, which will be item.a. Let's call it arg.a. Expression of arg.b, and then the source, which will be an invalid source. And then we define something with the function names. Well, okay, so it turns out we need to switch on the function implementation after all. Fun.impl, because that can be not an imported function, but it can be a built-in function. Comptime builtin, and it can be a something. It can be a, what is it? Toast, a local fun, sure. In which case we do this usual stuff. Yeah, let's call this result. Okay, nice. Oh man. Switch fun.run. Yeah, we need the context. And we do deal with circular calls, etc. Well, maybe. Oh, we do need the substitutions after all. Well. Okay, so this will take the substitutions. Sure. Module's not in scope, but we can change that because this is just fun module. Module is not a field, interesting. I see. Because this can either be a local function, which is... Oh man, let me take that, put that into here. Yeah, if it's a local fun, then it's fun.module. If it's a built-in, then it's just built-in module. And if it's imported, that is actually not, that's unreachable. Egg context. True, not yet. So let's add that. This also needs a stack, which is, let's see, a oh no way, the context has a module inside. That is, wow. Okay. Egg stack doesn't exist. What about, oh no, it's actually not imported. Well, oh yep, I'm just gonna remove that entire thing. As well as this. Totally fine, totally fine. Egg stack. So let's see how that pans out. Egg stack. Oh. Right, this is happening while compiling the functions actually in isolation. So this is not a property of the entire compiler. This is just a property of compile time evaluation. So we don't, that shouldn't be part of the context, I think. Or maybe it should, I don't know. Yeah, sure. Hell yeah, built-in, local, and imported is actually unreachable because functions are resolved before that. So run fun, line 45. What we do here, well, param is not in scope, that is true. We need the function parameter names somehow. And that, I think, is just function of params. Params is not a field, but this is a local fun. And from that, we can get the body. Oh yeah. Oh, that's a param. Sure. Runtime crash with a message. Amazing. Egg body compiler, we can't push an expression kind. True, we have to provide a type and source. The type of that will be type string, and the source will be the name.source. I believe. built-in of egg built-in. Oh yeah, that's not a thing, you know. So let's make that a thing actually. Let's say we have a new egg expression called built-in. Built-in call, I don't know. We could do like call lambda, call fun, call built-in as separate things. Yeah, let's do that. So here we have a lambda call, a fun call, and a built-in call. I mean, we could unify them to just calls, I guess. Yeah, it's kind of weird naming, like instruction. This is just like a fun call. Yeah, true. This is like call built-in. Egg.call fun. Stuff like that. Call lambda. Yeah. Okay, so there are errors in the playground. That is totally fine, by the way. Yeah, there should be a return type here, but there isn't. Sure. Okay, so we do something. Compile the built-in. What is going on here? It equals it. What the hell? That is. We have many expressions. I didn't expect that. Oh, I see. When like form a digit. Yeah, fair. That is kind of crazy. Yeah. So comptime built-in. Here. Yeah, what we want to do is basically run the built-in. And I know like this doesn't make sense. We don't need to do that. Please no. But this makes sense. Run an uncompiled function, and we can also run a built-in using some egg values as arguments and substitutions apparently. Mm-hmm. Okay, yeah, this, like, these don't have kinds. Don't need that. Because these are directly enum, so we can just say int.unwrap. Yeah, and here we can just say this is an add value.int. Which is even simpler than this purpose-built constructor. That is pretty amazing. What's it called? Name? Again, I'm not certain about that. Let's see, an enum has a name and a value, yeah. The value is, well, egg value.struct of an empty map. No types here, nothing. Boom. That's pretty simple, right? We don't need that. I don't even know what that's like. Why? We have this and ins, or ins, XOR. We have this thing. Oh yeah, this should be put on the heap. We concat strings, which will be an value string. We crash, which will do an early return of the message. We do type off, which is actually gonna return an value type. No, not quite. This will be, we don't care about the value actually. We'll just do substitutions.get t or something like that. Yeah. Do these fit on a single line, by the way? Maybe they do. Let's try that out. Does that entire thing maybe fit here? Oh, not quite. Sadly. Yeah, okay. I'm gonna leave it like this. Sure. Yeah, concatenating strings. Sure, we can do that. Yeah, crashing with a string, getting the substitution, getting information about the type. So what we do here, if, oh damn, this is kind of complicated. We don't need this comptime cast though. We'll just switch on that type and return different stuff later on. So in this case, it's just gonna be Well, yogurt value enum, so this will be egg value enum. Is that name? Oh yeah, because it's a primitive type. Yeah, sure. Mm-hmm. Mm-hmm. This one, pretty similar. You know what, let's create an egg value. Nothing. Maybe in the egg. Yeah. Nope. It's gonna be this. Cool. For a struct, there will actually be something in there. So yeah, the name will be struct, and the value will be an egg value list. Let's look at the yogurt for inspiration, I guess. Yeah, types, we don't need them. We'll just do that. If items get maybe 0 is some item, then it's gonna be egg value.enum. The name is more. The value is an egg value struct item maps to the item, and the rest maps to egg value list items subslide 1. Otherwise it's egg value enum of egg enum. The name is just empty and the value is egg value nothing. Put on the heap. And of course this up here is also put on the heap. Okay, yeah, so this is a value list. This one in here of some items of the fields. Which will be egg values, and for every field in the struct we'll put in an egg value struct of this. Amazing. enums, well, something slightly similar. This will just be, the name will be enum. Yeah, and then we'll have a list with the individual variants in the enum, and each of them will have a name and a type, which will be the variant, key and value. Okay, something like that. Yeah, lambda info of lambda is something we still need to do. Maybe I'll get some more tea soon. Yeah, comptime built-in. We don't use that yet. Indeed. So what we want to do is we want to take that. We want to just run that. So built-in.run with the arguments. Hang on, with the substitutions and the arguments. Okay, this call doesn't work. Get substitutions string. With substitutions we can not really do anything apparently, which is a pity. So let's do substitutions.substitutions.get for double the fun, you know? Oh. No. In the list, this should not be an egg enum, but an egg enum value. That compiles. Pretty cool. Damn. So what do we have here? Let's look at the main. Let's look for the main function first of all, and then see what we do. Then I'm gonna get some more tea, and then I don't know. Oh yeah, well, we don't use that in comptime evaluation yet. At least not for from the main function, apparently. So let's change that main function from this simple thing to this more complicated function call. I'm actually curious what happens here. Okay, make list. There is no matching function named compare ints for the args int. Okay, so make list is defined down here. That gets probably comptime evaluated, I assume. Let's also hang on, where's that? In compile fun. Yeah, when we want to comptime evaluate a function, I think we should also just compile the function in general. Just so if there are errors in that function, they get reported first, because like this is an error that's completely detached from the actual code. Yeah. So if the function should run at comptime, then compile the function first, just to make sure that there are no errors inside. If there are, they should be fixed. Yeah, this is not super efficient, you know, we are like compiling functions multiple times in the end, but that's, for now I'm focusing on correctness. So we want some sort of compile of a function. Yeah. So I guess compile that function. So this would be fun. We could also just do fun.compile, which is a bit cleaner, I think. Using some module, but this should be the module that the function is inside of, which is, I don't know, someone need to get that. Then we want invisible by module and functions and types. The module may not be the correct one, I'm not entirely sure. Module's not in scope even. Well, that is kind of unfortunate. Hang on, why do we need the module in here? Like, is that... That does seem a bit fishy, you know? Okay, yeah, fair. So if there are types in that code, those types need to be resolved with regards to the current module, like relative to that. Sure, I guess. So here we have a local fund module. Okay, if it's a local fund, then we can do that. Yeah, that is fair. I think in the run function I had a similar problem. Yeah, getting the module from a function. Let's just say fun.module. Why not? And then create a function for that. I don't know. Okay, so module is just fun.module, which should work. And in here we should be able to do like fun.module as well. Hang on, the compile function, where's that defined again? Here. Yeah, okay, I guess. Wait, hang on, this is based on a toast fun. You know what, let's not do that here, but instead when running function, when running some uncompiled function and it is a local function, yeah, then we check that. Amazing. And that may return I don't like that. I really don't like that. Yeah, okay, sure. That may return an error. So fun.compile u.handle uncompiled fun imported. Yeah, local fun.fun, which is kind of crazy. Oh, and we already have the module here, so no need for that. Actually, let's put that after that. So just get the function first, then compile the function, and then actually like build the, compile the function, run the function. Okay. Okay, and this returns a result, so it needs to return an OK in the end. Inconsistent return types. True. In fact, I would argue we can even return an error here. But again, I'm not. No, probably not. I'm gonna say this is definitely a weirder part. Like having these kind of nested results. Maybe it makes sense. I'm not entirely sure. 377 and compile fun. I guess that is where we call run. Yeah, that may return an error that we might want to return directly because it first compiles the function. Makes sense. Not quite what I was expecting, but sure. Hang on, we're compiling equals. Found a match compare ints. Boom. And still that it attributed to the make int function. Why is that? I assume it's because it does this part right here. But it shouldn't. It should just be like, oh, this is a local function, so let's compile the local function. Strange. Really, really strange. Yeah, I'm gonna print some status. Oh, I already do, kind of, So I think I'll just do It's not really okay, so it is printing stuff. So we run make a list. I'm gonna put those found match things. I'll remove that, because that is kind of annoying. Okay, so we are compiling some functions. Yeah, that's pretty cool. And then we're compiling main. And because that called make list with 2, we can immediately run that comptime, run that make list function at compile time. So first we compile make list, which actually makes sense. And then we run make list calls the equals function, so we first compile the equals function. Makes sense. Well, okay. I guess that is weird. I mean, I can just fix that here, but still. Yeah, compare ins doesn't exist apparently, because, but we do import that. In fact, we import compare ins for int and int. Well. I don't quite know what to make of that. There is no matching function named. Of course, there are multiple places where that can occur. We have this one. We have this one. Oh, which looks kind of abandoned. I think we don't use this ever. And this one? Probably also not. So this is the place where things kind of fall apart. So we have these visible functions. is context of visible module of the context module. Then we have the matches. Kind of wondering me is that name.string and name.source, they are no longer you know, the name.string is apparently compare ints, but the source points to something that says make list. That does not seem right at all. At all. I don't even know how to approach that. Yeah, let's improve the error reporting here, I guess. So first of all, let's say, rather than just we have the visible functions and then we get all matches, let's kind of split that up into several parts. First, we try to get the name matches, which will be a list of tuples, I guess, containing a signature and a fun, I guess. For every visible fun, what we do is we do, well, we get the signature from there, and then the name has to match, otherwise we continue. Yeah, that's basically it. Oh yeah, and otherwise we push that. Boom. And then we can kind of do a sanity check, and if there were no name matches, then we can also print the visible functions, for example. cool. Otherwise, we just go over the name matches and item, I guess. Let's get the signature and the fun. We've checked that the name matches, so we just build constraints. We do stuff, get the substitutions, and then here we have the signature and the substitutions. And these are kind of like the full matches. Yeah, true. And maybe in here, let's also print functions with the correct name, but where the arguments don't match. Yeah, there is no have mismatched types, yeah, something like that. And then for every signature and the name matches, oh, hang on, for every item, I guess. Yeah. Well, let's actually redo some of this work. Hell yeah. Yeah, maybe not. Maybe not. I kind of don't like that this is, if you have a typo in the function name, just one letter. But there are functions with that wrong name, then it will still show you those functions. But yeah, I guess that's fine. Yeah, match against or first of all, just print the signature. And then can we print constraints? Oh yeah, it's an uncompiled fun. True. Yeah, writing constraints probably. Yeah, but that is fine. Actually works. Dang. Sure. Ooh, this is cool. There is no function named compare ints in scope. Visible functions and boom. Okay, so I guess compiling equals works, but running it doesn't work for some reason. Because probably what we do is we say run that function with these substitutions. Okay, that should actually be fine, I guess. But then we ask for the module of that function. It's currently running. Where's that happening though? When we're running a function, we get the module. After compiling the function for that module, we then say, please compile the function body with this context. Okay, so I think we'll need to change the context module here. Yeah. Or rather, the module should just not be in the context. I think that's better. Yeah. So we have the body, the module, we know which functions are visible, and other stuff. Okay, so this is compiling a function. Well, that's just compiling types. This gives the module in there, this as well. Here we need to pass the module as well. Same here. Same here. I think. Same. Oh, that's just the type. Same here. here and here. Yeah, so in compile from line 22, we do this. Compile. Yes. Does compare ints get resolved? No, maybe. Okay, so something is not comptime, although it should be. That is fair, I guess. So we do get comptime. And here, yeah, when compiling the body, something will actually need to look at that. Like, you know, switch on the body. If the body is maybe a comptime value, but it may also not be. It may, for example, be a panic. I don't know if that's the case here. I don't know. Yeah, let's just print that and see what happens. Oh no, the program panicked. So this is not comptime. We have a switch in here. Well, and even though the condition is the condition is comptime, that switch doesn't get comptime evaluated. Indeed. Yeah. I don't quite know what to do here. Well, I do know what to do. To comptime evaluate the switch, but it is kind of weird that these things, they seem so intertwined. Maybe that makes sense, yeah, but still. Like, I'm wondering if there is something I can do to like radically simplify that. It does feel like I'm just like this is just messy, you know? I can't quite put my finger on it, like why I dislike the current approach. Yeah, let me make some tea and then I'll see what I'll do. do have nice hot tea. Amazing. Yeah, switches. Comptime evaluating switches. Ooh, that would probably go somewhere here. Case switch. Yeah. Recompile the condition. Yeah, we need to do that. Should do that. No. Compile the individual cases. Yeah. Here we just have case compilers. We build the cases, we bring them to the same. Oh, we do actually propagate the comptime condition value into the case body. Yeah, okay. So we'll just need to in here we'll basically need to check if the condition was compile time known. Then we won't actually put a switch in there, otherwise we will. The types of these will be the same actually. So this is just the condition kind that is affected. And in this one it is a switch, and this time it's a comptime value. So something like this. Oops. Yeah, expression kind comptime, and then we'll need to get the returned expression from the cases dot get body get comptime. The variant that it actually is oh, this is the value name. So we know that is the name. Yeah, sure. That is body dot get comptime of the condition, and of that is a value, right? Yeah, we know that is an enum that we can unwrap, and we'll get the name from that. So this would be name. And that case is a body with a returns expression that we can get from the body compiler. And that again should be a comptime value. Oh, that is nice. That is really nice. Okay, so now I think this one fails. So let's print something here. chosen switch branch equals to body.get. Yeah, should debug print that, because why not? Why not? Amazing. So the chosen switch branch evaluates to this one, a cast expression. Well, the type is true or false. Okay. Yeah, that is nice, I think. So for cast expressions, I think I'll actually... Cast expressions are kind of weird in general, because first of all, we don't want to cast values if the types are the same. And second of all, casting of comptime values should always result in a comptime value instead of an actual cast expression. So everywhere where we do like add expression kind of cast, everywhere where we do that in these two places, we should actually special case that. So what is this? This is the switch. These are the switch cases where we look at what those where we cast the result of them. And the other one is probably when calling a function. Yeah, when calling a function with comptime known arguments. Yeah, we kind of cast those to the expected function type, which makes sense. Oh, hang on. Oh, here we actually special case that. If the body is comptime, is a comptime argument, then that becomes a comptime value, and then we cast that. Otherwise we cast that. Yeah, that makes sense. And let's do something similar in the other case, in this case. So the returns, yeah, this is the kind, and then we just push that kind being the actual return. Amazing. Oh, this is a new error. Infinite comptime recursion. That is not what I expected, to be honest. But sure. It's infinite comptime recursion. Let's maybe print the recursion. Let's print, and in fact let's print all the stack entries. So let's create a string builder and then write infinite comptime recursion, and then for every entry in the context stack entries, we kind of want to print that entry. And then finally return the entire resulting string. This is not possible because the entry is its own thing. It's with the stack entry stuff. Does it have? Please have a signature. Well, okay. I guess at least debug print that. Not the most beautiful error message, but it will do. so we're running comptime recursion, running playground.make list of some int. I don't quite know what to do about that though. Infinite comptime recursion running some, make list thing. Oh yeah. If we run something, the make list function is recursive. So we don't just want to put this signature into the space there. We also want to put in the not this, but actually the arguments. Oh, I see. So for arg in args, I guess, do b.arg. Yeah, print the arg values. Oh damn. What is going on there? Is that an error? Hopefully. Maybe. I'm gonna Control C that. I mean, hang on, how is make list defined? Playground.plum. We do make a list. Yeah, fair enough. So I see. I feel like we had that at some point. Even though, at some point the list is 0, we still analyze both branches, and we need to do that to figure out the return type. We'll need to do that to figure out the return type. Does that make sense? Yes, I think it does. I'm afraid it does make sense. Okay, new plan. When we want to comptime evaluate a function, we just compile that function, and then we kind of run it or interpret that resulting egg. So we compile this function completely normally, and we do that we already do that, and that works. And then we're like, okay, main A is something, and then we walk that egg basically to evaluate this part. Yeah, that might not work. I mean, the question is, what about functions like these ones, you know? But again, when compiling a function, like parse JSON comptime, we just compile that function. And then run that function. I think that makes sense. The question is only when, like, if that function, if we compile that function, and then that depends on this function here. Like, let's assume we have two of these functions where the return type is inferred. We don't support them yet, but I want to support something like this at some point. So let's say we have two of these that kind of call each other. I mean, I think you should still be able to analyze them in isolation. Actually, yeah. So because you should be able to analyze them in isolation, even if the we'll have something like this type is unknown, you know. Well, I'm not sure that works. I don't like that. And I also don't like reducing the switch to, like, the switch should be cast to the original, to the same type as when the function is not compile time evaluated. In the, you know, something to yogurt code, I don't like that. I think we don't do that here. Yeah, if the condition is compile time known, then we only compile the corresponding branch. This is kind of, nope. I want to compile all branches to find the common type. And then even if the condition is compile time known, then, like, even if it's, you know, you have some function, one type, like one branch returns true, the other one returns false. The result of that should still be a compile time known value of true, maybe, but of the type bool. And if you then later on ask what's the type of this, you should still get the bool. And when you use functions, you should, like, those should be resolved the same way as if that function was called during with runtime values. Like it is possible, for example, to write some sort of function like this. a sum function that works on empty, and it returns an integer, and it always returns this, for example. Now, it would be weird if you can call this main function with a runtime known int. This is all commented out. This one. So, let's say you have something like this, you know, and this creates a list of the type empty or more. So the sum function refers to this sum function over here. But it would be weird if you then comptime call this main function with 5, and suddenly it doesn't compile anymore. Suddenly this is ambiguous because maybe you compile it with a 0, for example. So this creates an empty list. But the type of that should still be empty or more, even though we know the value. Because this function call should still use this sum function. It shouldn't be, you know, just because we know more information, that shouldn't make the code invalid, because now it's ambiguous whether the sum function means this implementation down here that only works on empty stuff. So even if values are comptime known, if I have a switch in here, like make list is just a big switch, I think, yeah. Even if I have a switch, I still need to analyze all the branches in order to figure out the common type. And the egg to yogurt compiler didn't do that. So I think I'll need some sort of generic way to analyze functions. And the only question is, what if we have two functions of this form that call each other? Can we even analyze these? Like if you have a function foo that, I don't know, accepts an a and returns something, and a function bar that accepts an a and returns something, and this function, you know, this indicates that the function can only be called at compile time, with a compile time known a, or like a string maybe. Which means you might be able to call something like this one right here. Parse JSON comptime of this a. That is supposed to be a point maybe. And then you do, oh, we don't have bar in here. And then you can just do pulse.x or something. So this returns an int. Or if this is a JSON, you know, if the JSON string here, if the x in there is not a number but is another string, for example, might be, then this function will return a number. So really the return type of this depends on this one. But what if this is actually bar, you know, and bar returns something? You might say, well, okay, before you do anything, you need to, like, first of all, writing something like this is invalid, because, like, this should be invalid at least, because this calls bar with some a, that's fine, but a is a runtime known string. So this one right here, this can only be called with comptime known values. That's not valid. So the only way to make that valid is by saying this. By basically telling the compiler, well, this will only work at, this function will only work at compile time. In that case, the compiler will still statically analyze this function to be like bar of a, and I think this still shouldn't work. I think. Not entirely sure about that. Maybe that should work. Actually, that's a fair point, right? Maybe that should work. I was like, my initial impression was that yeah, this would be kind of weird. So now the type of this is, well, we will still analyze this function, I guess, perhaps. But the type of this will be unknown. We'll have some extra type there. It just says we don't know the type of this. And as a consequence, the type of this here will also be unknown, which is totally fine, I think. The question is only, what do we do for like calls? Like, I would find it kind of weird if you write bar in here, and then you have another, you have something like this, and depending on the string that you pass in, this may either be an int or a string, so this might call one of these. Like, this is weird behavior. Oh, sorry, I mean, like, this is like parse JSON or something, and then we call some bar function. But the type of this is only known at compile time, but not when looking at this function in isolation. I think that is weird. I think I don't want to allow that. I think even, like, you should be able to look at a function in isolation and figure out which functions are called. I believe. I'm not entirely sure. So the type of this would be unknown. The type of this would be unknown, and that means you can't do .x on that type. I think that would be fair. You should maybe be able to have some sort of explicit annotation, and then that basically has a type. And then later on, when you use that function, that will actually be an error if that results in a different type. But yeah, that would kind of mean that we can compile this function in isolation. To, like egg, egg calls and egg stuff. Yeah, okay. And then, let's see, here we have this bar thing. I'm not entirely sure about that one. I'm wondering what if this bar of high, which seems like it's fine, but then bar calls foo of a, for example. Now suddenly, while we are analyzing foo independently from other functions, we'll see, oh, we call this bar function with high, so we'll need to analyze that bar function. First analyze that bar function, compile that, and then call that function, basically interpret that. But what if, what if the bar function does this? So we first compile this bar function, and that in turn means that we need to compile the foo function for this constant. And we need to immediately compile time evaluate that. Immediately. Because the result of these kind of comptime known calls that are self-contained in the function and do not depend on parameters, you should definitely be able to rely on those and call functions on those, like here. Because this string is not a parameter that gets passed in here. The string is just used and defined within this function. So you should then just be able to be like point.x or something, and have function overloading available and stuff like that. And to get back to the point, that means that we cannot even analyze foo and bar independently. Like first analyze the functions and then only then run them. Because that semantic information, like what bar does this, or like what flips function does this refer to, that depends on the type of this. So in order to do function resolution, we need to intertwine that with compile time evaluating this, which might then require compile time evaluating this again. So we cannot just compile time, compile a function and then compile time evaluate the resulting code. We have to intertwine that. I am wondering though, what do I want to happen in the switch? Because that is kind of weird, if we have some value here that is compile time known, and we switch on that, and there are calls happening here, like down here, for example. In general, the semantics of the yeah, what if make list returns that kind of thing? So it can only be evaluated at compile time, which would be totally fair. But then in order to figure out the type of this entire thing, we may need to call make list another time. Like we need to know the type of this one. So we need to comp time evaluate make list of len -1 regardless of the length. That just doesn't work. You can't have recursive, oh okay, I see. You can't have recursive functions during comp time, but well, at least you can't use type inference as nicely in this. I think maybe it doesn't make sense to say that inside of comptime functions switches behave differently. There they only compile the necessary branch, basically. That might make sense, yeah. Yeah, okay, you know what? I think I'm going to just not analyze these kind of comptime functions, or at least analyze them differently when I introduce them. And yeah, maybe those are not really type checked, but only when you use them. I think that's actually fair. Maybe. Let's do that. Let's do something like that. Keep it simple. Yeah. For now though, we don't support them, which makes our life so much easier, because then we'll just compile, we can just compile a function, and in run fun, we can actually just compile the function, not just as, you know, an optimization or something, as something where we are like, well, we want to, you know, check the function and then kind of build that same function again, but with comptime folding. No. Instead, what we'll do is we will compile this function that results in something in, not an egg ID, no, in an egg fun. And then, okay, this is actually cool. Now we can kind of run that compiled function. I think that's actually a clean architecture. Pretty clean, yeah. I like that. So eggfun impl.code, we know that's what this is. So we do, the impl is definitely code. We can unwrap that. That is an egg code thing. Yeah, and that has a body. So let's maybe just, instead of, you know, tracking this and basically recompiling that, let's just do some sort of, I don't know, run egg fun. An already compiled egg fun with some arguments. Previous slice or egg values. Yeah, I think that's fine. maybe also substitutions. Yeah, substitutions will be substitutions. Boom. Yeah. So what we'll do is, rather than building some graph and doing stuff, we'll just, I think we'll keep around a list of types, which will be a map from egg ID to plant type and values, which will be a map from egg ID to an egg value. And then for we'll zip the arguments. Yeah, sure. The fun params .iter, I guess. Oh no, hang on. Let's pull these into some sort of run state. Some sort of, run a body, egg body. With types, hang on, with a state, which is a run state. I like that. Yeah, that has a result of comptime result error. And actually this will also take arguments. Because the body has arguments. Makes sense. Runner, maybe? As types as values might also need some sort of let's call this like run, no, not context. Yeah, let's call this run state. I think that's fine. Okay. Yeah. And running a function creates a state with types and values inside. And the body takes care of zipping the body parameters to concrete egg values. need some sort of define. I think we don't actually need the types of these individual ones. Maybe, I don't know. Nice. So what we do in here is we just do state.define .b. Nice. And then for id and body.id. Oh yeah, this is what I wanted to do. In the state we also want the code. We do body dot state dot code dot get id dot run. Amazing. So we also have a run that works on an egg expression. That's amazing. So this call doesn't work. Define on run state. Oh yeah, because this actually needs a mutable run state, just like this does. Okay, ID is not a field on egg body. Yeah, it only contains these fields. Oh man, I think it makes sense to run an ID even. Because we can just get the expression from the state. Yeah, maybe even replace that. Perfect. So ID is not a field on egg body. It contains params, yeah, expressions, yeah, returns. That's pretty cool. That is pretty amazing. Yeah, so this entire thing returns a comptime result. Let's maybe look at that. It either returns something, an egg value. I mean, comptime errors, I'm not sure about that one. Because this already is an error. So in comptime error would just return an error. I think that's cleaner. And a runtime crash. That is difficult. Let's not deal with that now, but only later. And just say that this returns an egg value. I think we can live with that, you know. think this should just return an error. With a string. We don't really have a source though. So let's just do something, you know. Yeah, I don't know. We can make this, we can complicate this for better error reporting all day long, you know. But I first want to get something that is simple and works. Yeah. So defining something, sure. Running a function, it should actually result in an egg value. Running an expression, same thing. Running an body and an ID, yeah. And same here. Beautiful. So we get the expression, and I think then we'll just switch on the expression. Makes sense. Oh, on the expression kind. Should be unreachable. Oh, if this is a comptime value, then we'll just return that. I think OK is the default, so let's grab that. Struct with a all the fields. can be conservative, so just that, I guess. I'm not entirely sure about the lambdas. I do know that we're probably not going to use the types though, so that seems fair. Okay, so all fun. actually easier and more consistent if we treat crashes like values, because then we can just pass them around. We can check it. Here we call some function is the result comptime known that includes a crashing thing. And even if we see something like we construct an enum or a struct or something, and one of the fields crashes, we can just put that in there, and then later on we can still see, oh, this actually crashes. So I think egg values should actually also include crash, which sounds weird, but I think it makes sense. It's not really a comptime. There's some result, you might call this not value but comptime result. Yeah, some comptime known result of some computation. And yes, that is often a value, but it may also crash. Amazing. This is really amazing. This is so cool. So cool. That is crazy. Future proofing. Actually though, can we compile built-ins? I think we can. I think we don't need a special case step here. Yeah, but instead here. this is handled using the question mark. And it just always returns something. Yeah, even here, like this is not a built. Yeah, built-in is fine, I guess. But the actual part we want to have is that. Just that. Okay, so this compiles. I'm very interested in that. Here's the main function. Okay, it calls make list with the arguments. Well, I think it doesn't actually use the new code yet. Oh damn, I'm a bit scared, to be honest. Let's see what happens. Oh man. Oh, that is actually true. So in the switch, we put one value in that case body. But depending on whether you want a binding for that or not, you either take 0 or 1 values. Both are fine. So I think we'll actually need to get the case body first. That's just that. It went through. That is crazy. Okay, let's see. I'm kind of excited. It's like 1 o'clock, so I should get to bed. Here's the main. It works. It fucking works. Oh my god, this is so amazing. Damn. I mean, just wow. Just wow, honestly. Wow. What? That is crazy. So just for reference, until now I haven't really figured out how to deal with compile time evaluation in an elegant way, where I don't duplicate a lot of code and where stuff like this, you know, make list of 2 should be compile time evaluated like this. The main within this main function, this call of make list of 2, we should be able to depend on that to do some sort of, I don't know, something crazy. Yeah. Like this is guaranteed to be compile time known for the rest of this function body. That's the point. And at the same time, this here doesn't get evaluated if the other branch is chosen, but the types of both branches are still used to infer the type of this expression. That is crazy. That is honestly super cool. Crazy. What? That's crazy, yeah. Amazing. Just amazing. Yeah, cool. I think that's it for today. Well, turns out I was wrong. Well, this is impossible to analyze with the current approach. So here we have 2 functions, foo and bar. In order to type check that it's actually saying it contains, you know, here it contains this bar1 call. And per the Plum language semantics, you know, like if a function is called with compile time known arguments, then that call is guaranteed to happen at compile time. So in order to compile foo and type check foo, we'll actually need to, and you might say, well, bar returns an int, so we know that this is an int. That's true. But it may be that, for example, if this condition is, if bar appears somewhere else, I don't know, here, yeah, the result of that, then later on you should be able to kind of, at compile time, you should be able to call some, you know, compile time function, comptime something with that, and that should work. So compile time functions, this may be a function, you know, that is that returns something different, or you don't know what it returns. It returns something different based on the argument value. So here at this point, to type check this function to ensure that this returns an int, we need to know that this is something that makes this function return an int. So we need to know the value of that. So we need to know the value of bar1. And bar, to type check that, we need to know the value of foo1. And that is, even if this is just here. I mean, this is an infinite loop. I see that, you know. Foo of something always calls bar1, and bar1 calls foo again. So these always unconditionally call each other. But even if that's in here, currently we just eagerly evaluate these. We want to evaluate these. And that means that in order to compile and type check foo, we need to first compile and type check bar and then call bar. In order to type check bar, we need to type check and call foo. So what ends up happening is that when you try to compile that program, well, you know, yeah, stay over it. But we kind of don't, like, we're stuck in an infinite loop. So it's not that our implementation just sucks, but that the problem itself is this approach of, if a function is called with compile time known arguments, then that is guaranteed to be constant folded, and you can rely on that being a comptime result that you can then later on pass to a comptime function. That is just not viable, I'm afraid. I really tried doing this, but I believe it's impossible. So I need to think of some new language semantics actually, and then implement those. Yeah, I guess a kind of weaker approach maybe would be to basically have two versions, two different kinds of functions. Have these kind of runtime functions that you specify return value, and have compile time functions that don't specify return value, where, you know, the function returns anything, and there's an indicator to the compiler that you should only call this function at compile time and then just look what it returns. Yeah, then in order to compile a function, if we encounter a call, even if that call has compile time known arguments, we don't just by default evaluate that. Yeah. And on an additional note, like the question is kind of how do we first of all, like compile time functions, these ones, they are not analyzed in isolation. They are only analyzed when you use them with some value. So that should be fine. There's like, you know, kind of not dynamic typing because they do have types and they do, you can do type stuff in there, but they are not analyzed in isolation. They are only analyzed for concrete values, and that means that you can actually like you only do that on demand, basically. Only type check on demand. But these functions here, they are type checked eagerly. And in order to make that work, if there's another like runtime function being called, we are not allowed to comptime evaluate that yet. We can do that later on as an optimization, you know. You can't observe the comptimeness of that. That shouldn't be part of the language semantics. That would allow something like this, because this would just type check as new bar returns an integer, and this is an integer, boom, type checks. And then later on we can always say, oh, bar of 1, let's actually go and see what that produces, and stuff like that. And stuff like this would also work. You parse some JSON at compile time. You're calling some function that where we don't know what it returns, and that would work because here we see that this is not a runtime function but a comptime function. So this is evaluated. Then the only question is what happens if you do I don't know, this parse JSON comptime of this. So this is one string, this is another string, and we concatenate those two strings and then call parse JSON runtime on the result. First we'd have this plus call, and plus on strings is a runtime function, so this would not be evaluated at compile time, at least not eagerly. Because I think in order to support compile time functions here, we'll actually need some form of you know, compile time on demand thing. Basically we see, oh, there's a call of something that is a comptime function. Let's actually look at our previous expressions and try to evaluate them to comptime values. So if down here we say JSON is that plus that, and this is maybe, I don't know, FTS, some string like this. You know, and what we should be trying to do is we see, oh, this is a comptime function, so let's try to evaluate this as a comptime value. And if that is a we see that it's defined here, and it calls this function. So then we'll try to comptime evaluate the arguments to that function. This is a compiled unknown value, this not. So then we try to comptime evaluate this one. You see, oh, this is a function called, so we try to comptime evaluate the argument as comptime known. So then we do a comptime call of to lowercase, giving us a comptime result. And then we can do this call at compile time, then we can do this call at compile time. So basically, my idea is to kind of have these runtime functions, analyze them, general analyze functions. We can even do that in comptime functions, I think. You just analyze the function body, but for function calls, don't well, we'll see how that works in comptime functions, but analyze the bodies of runtime functions. Don't evaluate calls eagerly, but just leave them be, you know. And then if there's some call of a comptime function, then and only then kind of re-evaluate previous expressions to comptime values. And those may not depend on these parameters here. So this right here would work, you know. Just like getting information about a type or doing, you know, doing anything like these kind of things, they just work. But if that depends on a parameter to the function, then we'll actually say, hey, this call right here doesn't work because this is a comptime function and JSON is not comptime known. Because, and then we can even highlight the specific chain where this kind of depends on the parameters. We can say either you don't call this function, or you make it so that this is compile time known, by either making it so that this doesn't depend on the parameters anymore, or by saying this is also a function that can only be used at comp time. And then this is no longer eagerly analyzed, this function, only on demand. And then again, like even for only comp time functions, I think there was some, like, for example, we could analyze this, you know. I'm not entirely sure how far we can go there, but just analyzing runtime functions, I think, would make for a really nice language. It would basically, like, I think 99% of code, not a good amount of code, will just be normal runtime code like this. Like, this kind of thing is the exception rather than the rule. And that means that I think it's fair to, you know, within these functions, that they are not type checked. Sure, the development experience there is a little bit worse than it could be, but in all the other, like in the vast majority of functions, development experience is nice, like really nice. Being able to say, you know, just writing this and the compiler is automatically like, oh, by the way, you know, imagine writing this. And then you get auto-completion for X and Y. Like that is crazy. That is crazy powerful. Yeah. Okay, so I kind of spent the day doing something that's not quite working, but I do have a clear idea now on, first of all, why it's not working, and I know that this will work for certain. Like, for certain, because, oh, hang on. The question is, what if we call some function in here to lowercase, for example, and that depends on this function again. What then? And I'm actually not sure. should go to sleep and think about this a bit more some other time. Alright, new approach. Just leave comptime be for now and figure that out later. The runtime thing is the thing that's actually kind of holding me back from, you know, improving this language further. So, even though that I think this would be a nice exploration, and I do have, again, rough ideas on how I might make this work, but yeah, for now, just do, you know, the baseline should be being able to compile these kind of functions, period. Like, that should just work. So I'm just going to implement that. And then, you know, like introducing comptime functions, and then on demand computing values as comptime stuff, and like we can do stuff then. You know, you can this design, you can introduce that later on. Yeah. Okay, so that's my entire point. When converting something to egg, let me zoom out a bit. Yeah. I think I'll want to actually change the egg and simplify that. So the egg has a number of functions, makes sense. Those have a module, a name, parameter types, return type, and impl. Egg from impl has code, has a built-in, has expressions, sure. It has an ID, which we might call index. I think index is a better name for that, but I don't want to, yeah, doesn't need index. And then we have these egg express. Let's keep it at int and first fix the other stuff, and then add it through here. The expression kinds, let's not have comptime values as a separate concept, but instead let's put them in here. So we have ints, we have strings, we have structs, we have enums, we have lambdas, we have types. Okay, simple. Amazing. Yeah. And of course now stuff is broken, but that is totally fine. And I'm gonna simplify a lot of stuff here, a lot of stuff. This entire run fun thingy, I'm gonna comment that out and be like, to do, deal with this. The stack, I don't need a stack, I don't care. I'll remove. Okay, yeah. Let's see, we have types. This stays exactly the same, you know, compiling types. We have tracking which variables are visible, makes sense. Looking, gathering and looking up functions. Yeah. We have compiling functions, and that's it. That's it. We don't have any compile time execution by design. Okay, okay, we're getting there. At least now I have a clear idea of of a simple language. First, make the language simple. At least I know that the comp time evaluation complexity can be and should be contained. Yeah, this doesn't need a stack. Here we have the code compiler, sure. That does some stuff. We don't have these kind of things. These get a lot simpler because that is just int directly. Actually, I'm just gonna look for comp time and remove all mentions of that. Yeah, these are commented out, that is fine. This string is actually an expression string of that string. structs. We put those structs in here. We don't need to check for like comptimeness of stuff. Nope, we don't. And then we don't need this. We don't need this. Look at how much simpler the code becomes if you don't try to eagerly force comptime evaluation. And to be totally fair, like I want constant folding and optimizations. I want to do that later on, but by default, comptime evaluation of functions should not be part of the language semantics, I believe. Yeah, this is not a comptime thing. Simple. Simple. So much simpler. Damn. Yeah, switch. Yeah, to-dos, we'll still need to handle those. Then we have the switch cases, and they should be compiled just for the, you know, just for stuff. We don't need to worry about the condition being comptime known and then we assign a different payload. No, we can just say the payload is a parameter to the body, which makes sense. Then we compile them. Okay. We have these. Oh man, yeah, then casts, they just become runtime casts. No questions asked. Boom. This doesn't need that. It's can be inlined in here. A switch just always pushes a switch to the egg. Perfect. Then lambdas. Let's not do comptime things here. Oh, we don't. Yeah, okay, sure. Yeah, calls with arguments. We have the function name. Yeah, and this, if this is a struct access, this is weirdly indented, by the way, and that is always just a member expression, which doesn't even fit on a single line. That is very, very nested here. Yeah. Okay. Next comptime. Calling. We cast the arguments, yeah, by just emitting cast expressions for them. Obviously. And should run at comptime, no. And if should run at comptime, boom, just remove that. No, comptime execution makes the compiler so much simpler. So much simpler. So much simpler. Okay, here we have a lambda that just becomes a lambda call. A variable gets defined, these get compiled. Okay, let's compile that and see what happens. Oh yeah, egg. That is my neighbor upstairs. Oh man. Yeah, egg values, let's remove them. Well, we do remove them, so this doesn't make any sense. So then, writing egg values, that is not a thing. At least, not anymore. Simplifying. Egg stack, yep, we don't need that. writing a comptime stuff is also not a thing. Instead, we can write integers. We can write strings. And you can write types, which I think I put down at total bottom. Okay, so this function, this code now gets compiled. Yeah, let me go into this one right here. And I had these, yeah, let's kind of re-add these. Because this didn't compile before. Let's see if this compiles now. It does, and that makes sense. That is sane behavior. I want to look at the foo, the bar, and the main function now. So, well, here's the main function. It creates an int, casts that to int, because of course it does. And it calls make list of 2. Amazing. Calls sum. Yeah. That doesn't get constant folder, and that is fine. That should be an optimization at a later compiler stage, I think. Okay, here's the foo function, and it just calls bar with 1. That's totally fair. And bar just calls foo with 1. Probably. Yeah. Okay. Oh man. So where to go from here? I think let's just go to the next compiler stage. Egg to yogurt. So we have the egg. Instead of lookup, we should just be able to get the function with the signature. Damn. Okay. Well, egg entry module dot name, taking an int. And we don't need any of these, I think. Not yet, at least. Hang on, list. Type int. Here we have an entry module. I don't know exactly what's going on. I think I don't need this, to be honest. Yeah, that's not this for now. So yeah, we can always add more, like, you know, debugging stuff later on. Yeah, no, this is not really what's happening. Actually, let's not even have a compiler, maybe, because these two things in here. I mean, sure, yeah. Let's keep it there. Why not? So yogurt code compiler has the code that should be compiled, and then it has this mapping. Usually I just call this mapping. I think I'll do that here as well. Yeah, it's also called add mapping. So. And look up, we have a yogurt fun builder. So many concepts, compilers and code compilers and builders and so on. I think I can greatly simplify that as well. So compiling a matching fun. Matching fun is defined as having a function and substitutions, I think. Oh yeah, okay. So we need this, after all, to kind of figure out and, to handle recursive specializations of functions. If we specialize with some map function for a list T that calls itself, then we don't want to re-specialize that. We'll just assume that a map function for a list T exists. Why? Yeah. And I'll still have some sort of mapping here, I guess. And I'll have, let's go through this. We have a code function and we have built-ins. So let's put the built-ins before the code maybe. And here we have a yogurt fun builder. Okay. So we create a code compiler. Let's just see where things blow up, I guess. Let's say now we're creating the yogurt. Here's the yogurt. Okay, so we have some sort of get maybe. This doesn't work because it contains functions, and those functions have signatures. Oh yeah, just a string. Nothing more. And I think main shouldn't really be Question is, if we have some sort of main function accepting any t, is that allowed? Probably not. In the long term, I basically have to refactor how main works, anyways. So, because I kind of want to, I somehow need to figure out how to get into the program, and I'll probably not have an int, which is a bit random, being accepted as a parameter, but instead just have not even like the arguments like in C or Java, but I'll probably have nothing in there, just a main variable that you declare, and then that may return something like, please give me parameters and then call this lambda or something like that. Yeah, so this really should be, I'll refactor that. So yeah, now we're compiling the main function, but this is actually a don't compile with a yogurt compiler. I think the compile function, let's change that, yeah. Let's say we have just a function which will be a egg fun, and we have substitutions which will be substitutions, and then the parent types will be fun.parentTypes.specialize using the substitutions. Yeah, the signature will be the function name, and param types. Yeah, something like that. Oh yeah, that doesn't exist. Sure. We'll figure that out. Just find a name like this, maybe. Yeah, that is a string and source. That's great. Yeah. Okay, so we switch on the function, built-ins get compiled, code gets compiled. Amazing. For the code, we built yogurt IDs. We're going over the parameter types. Yeah. And basically creating a parameter expression in there and adding a mapping, stuff like that. Sure. Okay, then we compile the body with these params. Fun has a return type that we also specialize using those substitutions. Then we get the return type, those need to be assignable. Okay, body with cast is that. Let's maybe look at the yogurt and think how this will change. Yogurt fun. A yogurt fun also has expressions, but it should be kind of different from the egg. We don't have values here. Instead, we'll also have like ints and strings in the as operations, I guess. Here we have struct and enum, this, and type. Oh yeah. Okay. Okay, yeah, the yogurt becomes a lot simpler as well. The question is like, why do we even have this? I think at this point we'll need to kind of think how that separates, how that is different from the egg. From the main function, called functions are compiled to the yogurt. The generic functions are specialized for concrete types. Casts are turned into calls of casting functions. Yeah, that's what changes contrary to the what changes in the pudding. I think the pudding. Yeah, I think what would make things really cool is if functions like accept a like one thing that is pretty messy, I think, is the way that captured variables work and lambdas and so on. Maybe it would make sense to already put them into kind of simplify this in the way that functions just take parameters, you know, and a yogurt lambda actually has a function and then basically like a single thing that it captures, which is a struct. You know, basically the thing that we do when compiling to Pesto, that we already do that here. Maybe, I'm not sure about that. Okay, I don't want to change too much at once, so I think I'll just leave it at that and kind of think about that. Think about getting functions accept only a single parameter. You know, and bodies in general, and turning closures into explicit things. You know, turning closures into explicit structs, something like that. Yeah. Yeah. Like we have a lot of compiler stages, maybe kind of condensing stuff. I feel like because we do so much in the egg now, that is really clean, you know, doing like jumping from this one syntax representation to this other strong compiler stage that kind of has a clear vision, you know, only containing the stuff that's needed for the runtime execution, basically. That's pretty cool, but it does mean that these other compiler stages, maybe they don't pull their own weight, you know, maybe we'll have to remove one of these. I don't know. Okay, right, so egg to yogurt, let's go with that. We cast stuff. We don't have any form of comptime casts here, so this will just be, you know, I'll do one pass over this content where I just remove all comptime stuff. Yeah, we specialize generic functions for concrete types. We don't need to be careful about recursive functions. Functions being currently monomorphized. Yeah. Yeah. This, nope. Nope. Really simple. Really simple. And I mean, even the type, we can inline that here. Enum, that just becomes a yogurt dot enum. Nice. If the condition of a switch is comptime known, we don't care about that. We don't need to find a common type, we've already done that. We don't need to add cast expressions because we've already done that. We just need to compile the cases. Yeah, that is kind of weird. A call. Yeah, it's not a struct access, that is handled before. Casting the arguments is handled before. Checking if they are comptime. We don't need to do that. just have a call. I think we already have these instructions in the egg. I think, I'm not entirely sure. Yeah, we have this call built-in, egg built-in call, and that's actually just an instruction. And instruction built-in, like, these are weird names, you know. I tend towards actually not having them, and instead say that, yeah, we have these built-ins. These are the main built-ins that, you know, the language has, and then I think these get simplified and some of them get removed when we move to the egg. So we'll have egg built-ins. Actually, stuff like type info and type off, they still appear here. Okay, I think this is actually just built in. That's cool. But then in the yogurt we don't use instructions, but instead we do what's called built-in. This will not be a built-in, but a yogurt built-in, which is kind of a subset of the built-ins, where these two, they don't exist anymore because they have been kind of, you know, monomorphized, and because functions are now specialized for concrete types, we can execute these directly in the compiler, and they don't no longer exist. So it's only this. Yeah. Yogurt built in, and then in here you can say yogurt built in. Amazing. Actually, I'm gonna add it to do here, you know, remove this. Okay. Yeah. So egg to yogurt. Really, this doesn't exist, I think. Compile built-in, I mean, yeah, I guess. Yeah, but the function cannot just be an a built-in function, can it? Let me see. A function is, oh, it can be a built-in function. let's not do that, actually. Let's say that a function just has egg code inside. I mean, then it also doesn't really make sense to have these in here, because you can't just say, you know, function dot code dot expressions dot get function dot code dot body dot params of those IDs to get the corresponding expressions which have a type that gives you the parameter types, and same with the return value. I think this becomes really simple. Really, really simple. I think so much of this is gonna just disappear, I think. Yeah. Okay, so in here, this doesn't really exist, but instead we just have the code, which will be the function code. Yeah. So we have call fun, we have call lambda, we have call builtin, again just get the arguments, do stuff, get their types, I guess. Which we don't really need, to be honest. Well, we'll see how it goes. Yeah, we'll just emit that. Yeah, but we will just switch on the call builtin, and this is pretty cool. Dang. So we'll need to switch on all of these. Well, maybe not really cool. I think in that case we'll just call the yogurt builtin. In this case, the yogurt builtin dot subins and so on. And these other two, they will be different. If we are asking what is the type of some expression, we'll compare it inline and here. Something like this. And here we'll do something different, basically, like let's convert this into a folder as well. Just to simplify things a bit. And then the entire casting stuff. Okay, this right here. Yeah, that is a lot. That can just be moved to its own file. That's pretty cool. And here we'll import what also and we'll have some sort of compile fun, I guess. It's gonna do this. Okay. That's really cool. Nice. This is really nice. Yeah, let's see where the arrows come in. Oh yeah, these don't really exist. Yeah. Yeah, rather than when compiling a call, we'll have to check if that's the built-in function and then special case that, which is more sane, I think. So let's see, we have some sort of call. Yeah, this may not work. Yeah. So here we'll need to have built-in functions. We ask for the signature. Then we build the actual signature, which will be a string. signature.param types, and that is this signature's params. Yeah. Convert that to a string. Instead of putting a function somewhere, we'll just, you know, emit, kind of like we special case the struct access. Yeah. We'll also special case calling built-in functions. Like this. Yeah. Oh yeah, this needs substitutions. There is not. Hang on. There is not, no. Oh no. There should be. Let me get that from the version history, I guess. Like this is something I want. Yeah. So here I think we'll just do compile cast fun. And that needs from and to and a compiler. Luckily we can figure out our own type here just by saying, you know, expression dot builder. Maybe not, but we can say compiler. Okay. No, expression dot type. Yeah. Dot specialize using compiler dot substitution. Yeah. And this would then, hang on, substitutions is not a field, only contains, it contains parent, and that has substitutions, I believe. Maybe not. Maybe not. Oh, the compile function takes substitutions directly. Indeed. I think the expressions should do so as well. Perhaps. So substitutions is not a field on that. Nope. We'll have to pass them in here explicitly. Now we already know the type though. So we just need the hang on. Yeah, I think I want to restructure this function a bit. Rather than getting the ID and then in the end pushing that. I think the individual cases should take care of pushing the ID directly. And also, you know what, let me refactor even more. Let's say I have a general like DAG. Yeah. Like a directed acyclic graph. We define IDs that just have an index, and we have this tag which contains nodes, which will just be a list of something, because this is generic over T. And what you can do is you can say new node, returns you an ID, because what it does is it gets the ID is just the DAG nodes len, then it pushes that, and then it returns the ID. You can get a new ID. Sorry, you can get an ID. It returns you some T, because that just does DAG nodes get ID. Boom. Like, this is a very generic DAG. Also a constructor. Maybe let's call this put. I like that. So we have a DAG of T, returns you a DAG of T, because what it does is it just creates a DAG. This will be inferred when nodes is a list of T. Mm-hmm. Yeah, that is simple. And I think in the egg we can then simplify things, because we can just say that, well, yeah, first of all, we don't need these. True. And we have a DAG of egg expressions. And a body instead of this thing. Yeah. And instead of having this ID, we just use this egg ID. We just use the ID directly. I think that is fair. Nice. Fun has a module, it has a name, it has a DAG of expressions, and it has a body which has IDs, expressions, and a return ID. Okay, and these refer to DAG ID, but really these would just be IDs. That's fine. These expressions, rather than a kind, I think I want to call this op. For operation. That is simple. That is really simple. Okay, yeah, oh yeah, this should be in the DAG module. We shouldn't need this, because this exists in so many compiler stages. In the egg, in the yogurt, in the pudding. Yeah. We go to the function, we take the function body, not code.body, no, just function body. Yeah, using the function dag. Hell yeah. So we can print an egg body using a dag. Amazing. And then when converting something to an egg, what we really do is we collect all the functions, we compile them. Yeah, I think that's actually fine. And then compile fun. Yeah, we have this general purpose dag now, which will just be a dag of egg expressions. And I think then we don't need these, you know, code compilers and body compilers and so on. Because really, what is a code compiler? It's just a dag. It's just a list of expressions. And the body compiler, yeah, we don't need that. And instead we have this builder body. No, I don't know. Body compiler, sure. It's more like a body builder, I guess. These should be called either, like, these are not expressions, these are just IDs. So either IDs or children or something. A body contains children. Then we have push param. With a type, and source returns an ID, and that just does body.dag.put egg up. parsing an expression returns an ID body.children not push. That is pretty cool. Yeah, then also type of some ID is body.get ID dot type. And the source of something is that. That is nice. That is really nice. Okay, we have a bodybuilder as a separate concept, and then this is the actual compilation. And this is type int. Amazing. Mm-hmm. Mm-hmm. Types don't match against something. Mm-hmm. Yeah, I think that is fine. Like the rest of this is fine. Okay. So here we have a name binding. Mm-hmm. Then simplifying the yurt. Was saying that every function, first of all, has a DAG. It will just be a DAG of expressions, and then it has maybe capture things, and it has a body, which has params, children, and returns something. Mm-hmm. Yeah, we don't need this, we don't need this. Oh yeah, this is also a general thing which we can use in here. I think it makes sense to unify calls, actually. Let's do that. Call what? You know, colleague, maybe? That is either a lambda or a fun or a builtin. And then here we'll just have a call. Clean. That is clean. Yeah. Like ID doesn't exist. here we just have a call, and we print the callee and then the arguments and the callee. Well, nice. This is simple. This is really, really simple. Yep, I like that. Yeah. At some point stuff will fail. And the yogurt code compiler. Let's see, we have this yogurt compiler, which has stack entries and the egg and the yogurt, like the context, basically the stuff, you know. Should I call this context? Maybe. Yeah, let's do that. Say this is yogurt context. And rather than having this right here, I'm just gonna create that directly. Yeah, I think I'll change this by instead passing these things around explicitly. I think that makes sense. Hang on, we don't even use that here yet. Maybe down here somewhere. Yeah, put that down here. that's just going to be a map. Yeah, they are not typed, but that is fine, I think. So here we have a context, which is something. Let's not do that. Instead, let's say we have a body builder. That's what was called body. Simple. And then we'll do fun.body.params.iter, and the param types that we have .iter, and yeah, I mean, that is also fine. Yeah. Oh, I see. So first of all, we want to build a DAG. And in there we want to put a parameter, which we then push to this list of IDs, and then we add a mapping from the egg ID to the yogurt ID. Yeah, okay. And then we say fun.body.compile yourself, please, for these IDs with this DAG, with this context. Yeah, that makes sense. So what we're going to do is we push some expression to the body that results in an ID. What we do is we just say body.dag.put expression that returns us an ID, and then we push that to the children. An ID which just gets the ID from the DAG, and then you can ask for the type of and stuff like that, but I'll add those when I really need them. Okay, so compiling a body with some parameters and substitutions and a DAG, no, hang on, a body builder. Oh, no, this would just be a DAG, I think. Yeah. These would be the children. do dag get, oh hang on, yogurt context. I think we need some sort of egg dag basically, which will be a dag of egg expressions. And then we can get the egg ID, compile that using I see. Yeah, we want to get that, we want to compile that on the current body. And I want compiling an egg expression. Using the egg tag. Yeah, also using substitutions and a body builder. And the context. That returns an ID. So we switch on the operation. That's a parameter. There is something. Otherwise, like if this is an int, we just push a yogurt op int. The type of this is already known to be this. We don't need any extra information here. So I think we just want to map the operation. Here we can just do type. Well, yeah. Let's do it the simple way. If we have a string, then we push a yogurt op. Put a string of that string with that type. If we have this, then we can do that. Boom, just a few types specialized. Which means we don't need to worry about them in here. We don't need to worry about them in here. Here we can just do mapping.get. Just tell me mapping is a thing. Mapping is not a thing. Mapping is a map from ID to ID. Yeah, then we can just get the field value giving us an ID. We don't need to care about the type. Just need to do this. That seems simple enough. We build up fields by just getting the field value that has already been mapped and putting that in there. Okay, here the of type, we don't care about that. We only need that to this type. We already have that up here. So we can remove that and that and that and that and that, and we just say body.push pivot op dot member of is that. Okay, yeah. We already have the type, no need for that. What we do is we map the name. Value type is not needed. This is just mapping get of enum value. This is just enum name. Like that. Yeah, for a switch. We know that this has already been done. So what we do is we get the common type. That's just a type. We don't need to calculate that again. And what we do is we take the condition. Hang on, is this needed? No, we just map over the switch cases like this. We don't need to worry about the types. We just say, you know, the params. Yeah, we kind of need to map the params. So first that's just a list of IDs, and then for every ID, in the case value, there's a body, so it has params. We basically do params.push that mapping. No, this is not already in the mapping. We get that from the egg tag. Or specifically, we get the type of that. I don't know. And then we something like that. several other stuff like the mapping and I don't know what, the body and stuff. No, really the DAG, I think. Body.dag, something like that. And then here we have the cases. In there we put the body. Yeah, we don't need the case types. Just have the cases here. Yeah, we lower all the cases, that's obvious. This is not needed. Neither is this, or this for that matter. Or this. Or this even, because we can just do that inline down here. Yeah, condition is just mapping that switch condition. Yeah, lambdas are actually interesting because they will be transformed. Lambdas get converted into top level functions and stuff, so that's actually cool. So we'll look at that later. And then we have a call, which is the same whether that's a lambda or built-in or function or something. Because either way will map the arguments. We make sure that the archetypes match the lambda type. We don't need to do that. And in fact, let's just switch on the collie. If that's a lambda, then we do that. If that is a function, then we do something else. I don't think these are actually needed. Well, we'll see. does that even work without the... Is that not used, maybe? Maybe. No, these are individual IDs. Okay, yeah. Call doesn't work. Body builder. It probably needs a tag. Oh yeah. need that. Neither does it need parameter types, by the way. Compiling a body requires many things. It requires the egg DAG. It requires the parameters. Weird ordering, I think. Parameters are a bit more fundamental, I think. So, yeah. I don't know. Params, DAG, substitutions, DAG, context. Oh man. So params dag substitutions dag context. Find the body to compile. This is the signature compile of an egg body. With a slice ID. Hang on, compile an egg body. With a slice of ID, a dag of egg expressions, this one. Oh no, it has 2 times the context. Yeah. So it just says bodybuilder, but it needs the egg, the dag. That's a yod expression. That is cursed. Hang on, 1, 6, 3. Here we have the body, the egg body. So what we do is, oh, I see. Well, yeah. There should be like a finish on that. Yogurt. Let's call this egg body instead, and this just body. This works on the egg body. This compiles that to the body. Also needs the mapping. Oh man, that is a lot of stuff. Whew. Body.finish with this. Although I do wonder, do we even need these? I think not. I think if we just have a mapping here, then things work out. Because we can just, you know, assume that these are that the body's parameters, they exist in this mapping, so they have already been mapped. Yeah, we just create a body builder on the DAG. Then for every egg ID, we create a yogurt ID by compiling that on the egg body with a mapping. And an egg DAG. Why is tab focusing this up here instead of indenting this? That doesn't make any sense, does it? Tab. What? Why would you ever want that? VS Code doing weird shit. Okay, hang on. So we compile an expression just down here with a mapping. Let's maybe make this a bit more let's sort these a bit more intuitively. We have a mapping, we have a DAG. To both of these we kind of append stuff. And then we have the stuff that we kind of treat as read-only, the egg DAG, and substitutions, and then the context. And I think similarly here, we can just have the mapping and a DAG. Yeah, we need that. Oh, well, no, here we have the body builder instead of the egg, instead of the DAG. That makes sense. And then we still have the egg DAG, the substitutions in the context. Yeah, okay. Damn. Then on that body builder we can call finish on whatever this inner body returns. That gives us a body that we can then put in here, like that. This calls that down here with a mapping, the body builder, the egg DAG, and the substitutions and the context. Here we don't need these, instead we'll just pass in the mapping, the DAG, then the function DAGs, the substitutions, and the context. Hang on, we have an egg body, oh, it should be a mutable map, but the rest fits, okay. How is tab no longer working? That is infuriating. Yeah, this contains kind. I think this should be op. So pushing something to the body builder should put something into the DAG and then push that to our children. Yeah. But of course body.children should just be a list of IDs. That makes sense. And we should be able to finish that. ID, resulting in a yogurt body. We're just constructing a yogurt body with children being body.children to slice, returns being ID, and parents being body.parents to slice, which doesn't really exist yet, but we can do that. Mm-hmm. True. Body is case. Yeah, which has a value which is the actual body, which we compile there was stuff missing here, like the substitutions, the mapping should come first, and other stuff as well, but I don't know, let's just see. So egg body, yeah, mapping, yeah, DAG, yeah, oh yeah, the original DAG. So the egg DAG, I believe, yeah. For a switch, and we could even do this. Case.p and case.value dot, you know, mapped. Amazing. And then we don't even need these, right? Please give me the caption variables given this DAG. Right? Yeah. do we even need the captured variables in here? Oh, in the yogurt. Yeah, okay, maybe we do. Yeah, I think we do. Fair enough. Yeah, captured egg IDs. We map them. Is this used somewhere else? Yeah, it is. Okay. Yeah. So the lambda. What is that? This will be a body building of a DAG, and this will be the lambda DAG. Yeah, and then we say lambda body dot push parent. We do inner captures. Dot push. Why do we need that though? Oh, yeah, okay. Let's call these outer captures maybe. I think rather than having these kind of scattered comments, it makes sense to have like a kind of explanatory comment up here. So first of all, lambdas get compiled into stand-alone functions. Period. That's already nice. Yeah. Then explicitly capture IDs that the caller needs to provide. Here we figure out which that's like general context. That's very nice. The egg IDs are no longer used, are they? They are. Oh, I see. Okay, yeah. I think we'll also need a mapping. Egg ID is something. Now you know what? Let's do this outside here. And in here, let's put this in here and merge that with these. And then these are no longer used after this, I hope. Yeah. So we can just inline that. Yeah. Oh, that is nice. Yeah, and in this mapping. Yeah, that is clean. Amazing. Yeah, so the parameters are then mapped. Oh, come on. Let me reload the window. Hopefully I can then... oh, tab works again. That is nice. Okay, so the params are the lambda params. Yeah. But why do it in such a complicated way? And the lambda is a body. The body has params. Yeah. Here's the lambda body push param. And here we have the egg ID. Hang on. The lambda is an egg body. So it just has I think we'll just need, we have the param singular, that is an egg ID. Yeah. And then we push a yogurt ID. like that. Is params used at some point? Yeah, it is for the body. That makes it doesn't make sense, because rather than doing it like this, we actually want to turn that into a body like this, like lambda body dot finish with something. Yeah. Okay. So we don't need these params. We'll just add a mapping. That will just be lambda mapping.put. Okay, so we have the params, then we have the expression, which will be similar. We go over the lambda that is already a body, over the children. This returns as the egg expression that we compile on the lambda body. And lambda mapping, like lots of stuff. Something like this. And then we'll do lambda mapping dot put that mapping. Okay. Yeah, then the lambda body will finish that using the return value. So lambda mapping dot get whatever that lambda returns. Then we say the signature is that to do new compile same number for different types. Okay, and then the context contains a yogurt oh man not at all complicated, not at all. And this doesn't make any sense, like this doesn't even relate to the content of this. Weird, really weird. Yeah, in the end we push a lambda. Oh yeah, the type, we already have that. We don't even need to figure that out. So that is nice. So this just has the captures is outer captures. And in the function is the signature. Well, captures. It has a DAG, which is just a lambda DAG, and it has a body. Yeah. Directly on the context. Sure, I can do that. $270. Try to send a list of ID to field captures. Why is that? Try to assign a list of ID to field captures. Slice of ID. Oh, I see. Here with the lambda 270 down here. Yeah, let's convert them to slices. Sure. Then down here we don't need that. And we can even simplify this a bit, at least. Okay. But are the archetypes really needed? Well, not really. Yeah, we don't really want to look up a function like this. I think. We do want to specialize the function though. So I think we'll have to do context dot fun dot compile or something. Yeah, similar to this. But we can just use context dot funs dot get fun, because this is just a signature, I believe. Yeah, we don't need the call name, we don't need candidates, and this is functions have already been resolved at this point. Call of a lambda. So what we do is we get the lambda ID, and then we get the type of that from here. That should just work. Is there a closing parenthesis there? Weird. I mean, the types are already matched. We don't need to do that. We don't need to do that either, or that. We just need to say, please call this lambda, or the lambda is this. Simple. The yogurt. Ah yeah, the yogurt still has this. But I think I want to update that too. Yeah, let's just have a single call, which will be a yogurt call. And then we have a yogurt. Some sort of yogurt call with a callee, which will be a yogurt callee. Either be a lambda or fun or built-in. Yeah, that simplifies things. Two 8 not here, but here. Context.funds doesn't exist. It only has stuff in there. I guess the egg has the funds, right? Yeah, that makes sense. Compile egg fun with yogurt context. And compile egg fun. Oh yeah, also needs substitutions. Apply substitutions. Because in this context we may have other substitutions. So oh yeah. I mean, we do have stuff for the parameter types. Yeah. So I think it also makes sense to have something for the return type. sense. Yeah, okay, then I don't even need this temporary variable. Oh yeah, that needs a yogurt built-in. That is true. Oh man. So I guess we want some sort of DAG, which will be a DAG of yogurt expressions, and then some sort of body, which will be a body builder of that DAG. Then we do body dot push parent of the from type. This is captured, it has a DAG, and it has a body, which will just be body dot finish with the return thing. Compiler is not in scope. True. It should probably be context. Yeah. Oh yeah, and an enum, we just create new body builders on the same DAG. So on that. I think I'll keep that. All types. Yeah, I'm gonna suffix all types get type. Yeah, that is great. And the param is just the from value. That is really consistent. Mm-hmm. Okay. I think this doesn't work super well. Fair enough. Okay, so lambdas and the rest will be in the next video. See you then.